So how many of you have heard about Udacity? Okay, cool. And how many of you have taken our courses? Okay, cool. So just to be clear, a lot of this material is based on what we develop for our courses. And this also gives us a good opportunity to teach in person and improve our content over time. So thank you all for coming here, and please let us know how you felt about the workshop, if you learned anything useful, how we can improve it going forward. So today's talk is going to be on natural language processing, but focusing on how we can use deep neural networks for natural language processing. We're going to start with fairly basic items. If you do have experience in that field, feel free to skip ahead and start working on the more advanced stuff. There is a link here to a repo, github.com, Adarsh0806, ODSC. If you check out that repo, that should have all the code in it. We've also included some of the data that you'll need. There are some libraries I think we mentioned in the talk description that you'll need to have installed: basic NumPy, scikit-learn, Keras, and TensorFlow. It's also included in the repo in a requirements file. So while we get started, you can get this process going so that you're all set up by the time we get to the portion where you're actually hands-on coding. All right? Everybody got the repo link? Does anyone need? Yeah?
Is Julia a requirement?
Julia, no. We're going to be based in Python, scikit-learn, Keras, and TensorFlow. Cool.
The information center will say that Julia also needs to be installed.
Julia? I don't know how that happened. I do have one USB. Can I? I do have one USB with the data and the repo, a local copy of it. Feel free to copy and pass around. But what we're going to do is start off with a quick introduction to the classical methods in NLP, things that you might have heard of, bag of words, TF-IDF, and what are the underlying mathematics behind that. And then we're going to do a lab, a hands-on lab in topic modeling using a modeling technique called latent Dirichlet allocation. It's really hard to pronounce and even harder to implement. But luckily, there are existing libraries that, once you understand the concept behind it, it's pretty easy to apply, and it does give you interesting results. So we'll go through that. Then we'll switch gears into thinking about how to apply deep neural networks for NLP. Luis is going to start us off with an introduction to neural nets, a very intuitive and fun way to think about it. Then we're going to talk about recurrent neural nets, which are very commonly applied in natural language processing. One of the things that we're going to highlight is about word embeddings, which play a critical role in taking text data, converting it into a form that neural networks can use. And finally, we'll conclude with a sentiment analysis lab using RNNs. Okay? So just starting out, I'm going to go over some very basic fundamental concepts of what are the main challenges and the benefits of NLP. So if you think of language, it's both a medium of communication as well as, yeah, go ahead. Okay, sure. Thanks. So if you think about language,
Are USBs being passed around?
yeah, it's over there. I can actually hear myself loud on this microphone. I don't know if it's. But anyway, so if you think of language, it's both a medium of communication as well as a way of thinking. That's why natural language seems to have so much information contained in it, because it's not just people expressing their ideas, but people expressing their thoughts or the way they're thinking, and there might be like useful information there to extract. And so where does this term natural language comes from? In order to understand that better, let's look at a few structured languages first, which are easier to parse and easier to understand. Some of these languages, are around us and we use them every day. One example is mathematics. And the idea here is that when you say something like y equals 2x plus 5, the meaning is very clear. You're saying that the variable y is related to the variable x in this particular way. Right? There is no ambiguity in it. This is the class of structured languages. Another example is formal logic, where this statement means if x is a parent of y and x is a parent of z, then y and z are siblings. And this is a statement, there is no confusion or ambiguity implied here. And this is how structured languages typically work. Other examples include SQL or programming languages. These are all languages, right? And if you think about it, for these structured languages, there is a specific grammar that you can use to parse and understand what it means. Again, to resolve any ambiguities. Same thing with English, but now we're getting into a little bit of a gray zone, because sometimes natural languages can have multiple interpretations depending on how you parse and break things up. Right? So, for instance, this statement is an example. Because he was so small, Stuart was often hard to find around the house. And the thing here is, like, we humans, when we read it, it's usually pretty clear because we are bringing forth a lot of background knowledge into interpreting this sentence. But for instance, what is he referring to here, right? Stuart, right? So it kind of makes sense to us. But if you think of it from a computer's point of view, sometimes these very simple sort of inferences are very hard to make unless they have the background knowledge that, oh, Stuart is a rat and rats are typically small, and that's probably what this sentence means. These are all things that we're constantly sort of performing all the time, these inferences and connections we're making all the time. This sort of gives you some sense of how complex natural language processing might be under the hood and why it's so hard for computers to properly understand us. There's some fancy animation. Right? So another thing is finding out or recognizing parts of speech. Again, things that we pretty easily understand over time. But sometimes there are conflicts that need to be resolved. Again, we apply a lot of background knowledge in order to resolve them. Okay, so one way of thinking about natural language is, okay, if it's so hard to parse and if it's so hard to extract meaning from it, why don't we just treat it as unstructured information? Like, let's not assume there is any meaning associated with it as such, any format or any sentence structure to it. Let's just think of these words as just a bunch of words, and let's see how far we can go with it. And it turns out that we can actually do a lot of things with it. For instance, we can assign different weights to different words based on, say, how frequently they appear or how rare they are, etc. We can assign some sort of sentiment or qualifications or properties to these words. And then when you look at a complete sentence or a paragraph or a document, you can then aggregate this information to extract some high-level aggregate meaning from it. Even though you're not really going to the extent of understanding what the sentence means, you can still extract some useful information. And this is what serves as the basis for a lot of traditional natural language processing that people perform. So some of the applications are, for instance, sentiment analysis or classification of documents. Another is here, you're trying to find out what topics are being talked about in documents. So that's another form of classification or mapping, going from documents to topics. And then translation is a very popular application for NLP. All of this, to a certain extent, can be supported by the techniques we're going to talk about today. So what are the main challenges in NLP? One of the things is, like, how do you actually split it up, and how do you relate the different components that you split up, for instance, a sentence or a document into? Like I mentioned, you could go to the extent of finding out what the actual entities are in this statement, what is being talked about, and what the relationship is between them, right? But this is pretty hard. Or another extreme is you could just turn this entire sentence into some sort of, garbled up vector representation and do something with it. We'll see examples of this later on. What could you do with a vector representation like this is you could take, for instance, two sentences and compute how similar they are. That might be useful for you. Depending on your application, you might need to do one of these things or convert it into a different form. So taking natural language and then converting it into a representation that you can use further down the road is one of the big sort of challenges. Like, what is the correct representation for natural language? Do you keep the words? Do you try to find out sort of meanings between them? Do you convert them into a numeric vector? And all this will depend on your application, what you choose to do. Another underlying challenge for NLP, unlike other forms of data, is that natural language is typically a sequence of words or a sequence of entities, right? And this is something that is less understood or less researched right now. So there are a lot of challenges related to that. For instance, if somebody says, I want to buy a gallon, right? Then this sequence, I want to buy a gallon, should enable an automatic, like a computer, to automatically infer that maybe we're going to talk about milk or water or petrol next. And so there is some meaning already encoded in the sequence of words that somebody has uttered. And so this sequence aspect is another challenge. Like, how do you encode this sequence? How do you say that, this sequence of words might lead to something new? It's not saying that you have a static sort of example and you're trying to map it to another static example. Here you have a sequence and you're mapping it to either another object or another sequence. And the last, or one of the subtle sort of challenges, which I briefly referred to before, is context. So sometimes the meanings of different words come out only in a larger context. If you were to read like a small chunk of this paragraph, sometimes you won't be able to tell what we were talking about or who we were referring to, but these meanings come out in a larger context. So if you have an automated system that's analyzing this, then it has to keep track of all these references in order to properly understand what's going on. Right? Cool. So this is a quick summary of major steps in natural language processing. So when you get like a raw sentence or piece of text, the first thing you have to do is process it, which might mean cleaning it up or changing or normalizing the verbs to the root form. Then you might have to transform it into like a vector or some other representation that you want to feed forward. Then you analyze it using some model, and this is where machine learning comes in, or neural networks will come in. The learned model can be then applied to test scenarios to predict or to utilize in whatever application you need it to, and then you would somehow find a way to present or use that information. This could be in form of recommendations, it could be in the form of visualization that you produce, but a typical natural language application goes through a pipeline like this. Okay. So that was a very general introduction to NLP. I don't know if it made much sense, but if you have any questions at this point, I can take or can move on. Okay, cool. So the first big stage in any natural language processing pipeline is text processing. Like you're taking raw input text and converting it into a more useful form. Now, why is this typically necessary? Two reasons. One, text is not, by itself inherently not numeric in nature, and a lot of our machine learning models are based on statistics. They need some form of numeric input. That's one of the reasons we need to start processing text. The other is that text, like especially natural language text, has a lot of variation that can complicate things down the road. So we sometimes want to simplify things. So simplification and converting it into a numeric form, these are two reasons we do text processing. Otherwise, we could have just taken raw text and thrown it in. The three main things we're going to talk about today are in text processing are tokenization, stop word removal, and stemming and lemmatization. I don't know if you have heard of these terms, but they're not as scary as they sound. So tokenization is simply breaking up a sentence or paragraph or whatever form of document you have into pieces. Now, how do you break up these pieces? There might be a little bit of decision you have to make. Like in this example, do you split on the apostrophe or do you just hide it and treat didn't as a single word? It sometimes depends on your final application, but more or less, either of these forms might work. Another thing is, do you keep the apostrophes and other punctuations there or not? Again, it will depend on your application. For instance, if you're looking for, I don't know, if you're trying to do some sort of sentiment analysis and you're mainly basing it off of words, then you can probably drop these punctuations. But if you're doing, for instance, machine translation, where some of these punctuations might need to be retained in the translated text or might affect what the translated text might be, you probably have to keep those punctuation marks around. So there are some decision points, but basically tokenization is splitting text into smaller chunks, which can be typically words. Here's another example. Do you split it in an entire document or paragraph into a single sequence of words, or do you split it into different sentences? Again, it'll depend on your application. All right, stop word removal. So what are stop words? Stop words are words that are very common in the language and might not carry as much additional information. For instance, if we remove these words, the, was, in, by, etc., and you just read wristwatch invented 1904, Louis Cartier, you can still sort of make out what this sentence probably means, right? And that's why, if you need to keep them in, for instance, for machine translation or other applications, because you need to keep that structure in, it's fine. But if you're doing something like, something more aggregate, like you're going from this whole sentence or a piece of document to a single value or a single decision, then you can probably drop these. And the reason to drop these stop words is not just because you can, but because having more words, having a larger vocabulary will lead to a more complex model later on. So when you have to tell a number of different things apart, then that increases your complexity. So that's one of the reasons we do stop word removal. And a lot of this is already sort of supported by libraries like NLTK, so you don't have to do all of this by hand. But what you do have to do is consciously think of whether we need stop word removal in my application or not, or do I have any special stop words? For instance, if you're doing a domain-specific, sort of dealing with a domain-specific problem, like, I don't know, in finance or something where the word money or price comes up, all the time, and it's not adding a whole lot of useful information to your signal, you might want to drop those. So you might need to customize the stop words for your application. And then stemming is basically when you have different forms of a word, especially verbs, you might want to reduce them down to its root form. And stemming is one of the more crude ways of doing it, where you just lop off the end of the word. And what this might lead to sometimes is a word that is actually not a word in the dictionary, but that's okay, because from the computer's point of view, this is a unique token, and it carries that common meaning that is carried by these different forms of the word. Right? Now, if you wanted to be a little more proper, you would do lemmatization, which is basically converting words to their proper root form. And here's an example where it would be really hard for stemming to tell that these words is, was, were actually related or carried the same meaning. But this is basically, you need a little bit more processing. You need some sort of mapping or dictionary to go from the different forms of a word to its root form or stem. All right, that's that. All right, so like I said, text processing, not too complicated. First step, split into words. Second step, clean, which might mean remove stop words, which might have some other additional steps, like you might want to remove punctuation marks, you might want to keep them. And then normalize, which is where you bring in stemming and lemmatization. Again, notice that you may not need to do this in all applications. I keep referring back to machine translation because it's a nice sort of different enough example. Like, imagine when you're translating text, you actually want to keep verbs and other words in their original form. You need the tense or the grammar to be appropriate. So you wouldn't really do stemming or lemmatization there, right? But again, if you're only looking for like aggregate meaning or some sort of high level analysis of the words, then it'll simplify your model going forward if you can normalize words to their root form. Cool. Any questions so far? No? Seems pretty okay. Everybody on board? So what do you do with this converted text, right? If you think of, again, going back to the idea of statistically modeling these things or applying machine learning techniques, you need to go from this. What we did in text processing was we chunked up or normalized the text, but it is still in text form, right? It's still, we haven't gotten to the part where we convert them into numbers. This is basically that. How do you take text and convert it into numbers so that you can apply it to a statistical or machine learning model? Two representations that are actually pretty related. One is bag of words, and the other is TF-IDF. We'll look at these two. And these are part of more classic natural language processing. Bag of words, as the name suggests, you take a document, split out the words, tokenization, and go through that text processing step, and just put those words into a bag, right? So every document would now be represented by this bag. Now, how do you write this bag, right? So one example is, now think of these sentences as individual documents, and this entire collection of sentences as your corpus, okay? So you want to basically convert every sentence into a collection of words. That's your bag. But sometimes you have this, like confusion. What if a word occurs twice? Or what if there are common words across sentences? How do you deal with them? So one of the approaches is to figure out all the common words across all these documents in your corpus, and then form a table of them, right? And then the task of converting it into bag of words is simply filling out these rows, marking wherever a word occurs, right? And when you have two occurrences, like in Twinkle Twinkle Little Star, you simply count it by 2. It's as simple as that. There's no like magic to this. It's very manual, but or very sort of procedural, but it works. There are some actual applications that you can do with this. And by the way, you can think of individual bags stacked together as a document term matrix. So you now have documents as rows and you have terms as columns, and this matrix is just showing you the relationship between documents and terms. So what are some of the things that we could do with this? And yeah, you can call these individual elements term frequency. So one of the things we can do is compute document similarity. Now you have an entry in every position. If you treat these two as two vectors, then you can compute, for instance, the dot product between these two vectors, which is you multiply each corresponding element and then you add them up, right? So wherever there is a 1 that is common between the two will result in a 1. So if you had more common elements, then the total sum would be higher, it would be greater. And if you didn't have any in common, then the dot product would be 0. So that's one way of measuring document similarity. There is another way of sort of like measuring similarity, which is cosine similarity. I'm not going to go into too much in that. Like you basically have two vectors and you want to compare the similarity between the two. There are a few different measures for that. But what I do want to focus on is, you know, so far we've only looked at the frequency of terms within documents, but let's also consider how many times a word occurs across the corpus. Now, why would you want to do that, right? Because that tells you how frequently that word occurs in your collection of documents. Like I mentioned before, you might have certain words that are very common, right, in your corpus and might not add much value to your analysis later on. So one of the intuitive things to do is use this number and then reduce the effect of each of these words using that number. How do you reduce the effect? One approach is to divide everything by the number of times that word occurs across the corpus. So you're sort of normalizing your vectors, right? So if you have some word that's occurring across multiple documents, it doesn't affect the individual sort of vectors as much. Cool. All right. Now, if you look at the vectors that have formed, and you look at the numbers that have the highest values, you'll start to see that those numbers correspond to the words that are unique in each of these sentences, right? So after normalizing, you can see that, okay, house and prairie, occur only in this sentence, little house on the prairie. Mary is something that is unique to Mary had a little lamb. Silence is unique to Silence of the Lambs. Twinkle is unique to Twinkle, Twinkle, Little Star. And so far, we've only been doing simple arithmetic, basically, right? We've been counting things, summing them, dividing, and already you have a representation that is carrying some meaning. It's representing what words are more unique, what words are less unique across documents. So you have something to work with. We can go one step further, and this is actually a variation of what you already saw. There's a specific formula you use, and there are reasons to do this, which I'm not going to go into right now. But the idea is very similar. You take the term frequency, which is how many times a word occurs in a document, and you take the inverse document frequency, which is a little bit different. It's not how many times that term occurs across documents, but how many documents that term occurs in. It's a little weird, but that's your normalizing factor. And you normalize all the counts by that, and you get a nice vector just like before, but it is better suited for analysis later on. Okay. Now, what can you do with this vector form that you just created? One example task is spam detection. So a message comes in and you have to decide whether it's a spam message or it's okay. Right? Oops, sorry. And the way you would do that is when this message comes in, you'll turn it into a vector, either using bag of words or TF-IDF representation, feed that to a classifier, and if you're familiar with machine learning or statistical modeling, once you have a set of numbers and you have a set of numbers for each input example, you can set up what is called a supervised learning task, where you're giving these vectors as inputs, and if you have labels on whether that message was a spam or not spam, then you can train a model to then start predicting whether something new is spam or not spam. And this is an example of a classifier, so you can think of this same technique being applied to other classifier scenarios. For instance, you might want to classify messages as having positive or negative sentiment, or as representing ads, or thoughtful content, whatever your different categories are. Right? But let me pause here and see if you have any questions. Yeah.
So what is the value of dividing that each number of occurrences, total occurrences?
Right.
What do you find it doing that?
So the reason we divide the counts by a word's total occurrences is to reduce the importance of that word. So for instance, if I go back to like this stage, or where we haven't divided those numbers, then you'll see that, for instance, little has the same significance. So in this representation, in the very first row, little, house, and prairie have the same sort of weights or values for this sentence. Whereas if you consider this sentence in the context of this corpus, here little is something that occurs in other places as well. So it might be something that is not unique to this sentence. It's not like a unique enough signature. So by dividing by the total number of occurrences, what the resulting representation is more unique for each document. And it might be harder to think about this right now, but the idea is you want to get basically a signature for each sentence or each document that identifies it as uniquely as possible, but at the same time also maintains relationships between documents, so that two documents that are similar should have a similar vector representation, but two documents that are different should have very different representations. So that's what we achieve.
And then this here is not the T.IDF, so what's the ID? So what's that?
Yeah, so the reason I didn't do that here is because the TF-IDF calculation has a log involved, and it's a little bit different, but conceptually it's the same.
Okay, so
So-
similar to this.
Yeah, it's similar to this. And actually, when people refer to TF-IDF, there isn't a single definition for it, right? What you do is you take your term frequency and you define how you come up with the inverse document frequency. Sometimes it's also a matter of practicality. Let me just skip ahead. That some of these terms can give you a weird number, because like you're dividing things and they might be zero, so people use like a one-off variation on these. Some variations don't put a log there, so there are a few variations of it. But yeah, the idea is that you're taking individual counts, and you're taking either counts of how many times the word occurs across the corpus, or here it's actually how many documents does that term occur in. And you can read up about this more to understand. I don't want to take up a whole lot of time. But yeah, I just want you to keep this overall picture in mind, that you have an input document coming in, you're converting it into a bunch of numbers, a vector, you're passing it into a classifier, and that is predicting something. It could be either like a class, positive, negative, or even a number that gives you a score, right? Yeah.
And then bigger the number, the more important word is for that document.
For that document, yeah. Typically, that's what the number signifies, but It could also be, like, depending on the way you scale things, this vector could have positive or negative numbers as well. Overall, what you need to think about is this is a signature of the document. So think of hashing, for instance. You have a document or a number and you hash it into like a fixed size form. It gives you a signature for that. Cool. So the next section, so the task that we talked about is mainly classification, which is a supervised learning task where you need to provide the model with your inputs and your known labels, which is, for instance, in spam classification, you need a collection of messages that you know are spam or not spam. You feed them into a classifier, it learns to then predict any new ones. Topic modeling is an unsupervised learning problem where, given a bunch of documents or articles, you want to find out what topics they're talking about, and you have no clue what those topics might be. So it's something that an algorithm should be able to extract from the data itself. That's why I wanted to discuss this application. I find it pretty interesting. And the central concept at play is of latent variables. Latent kind of loosely means hidden. So in topic modeling, what we're saying is, here's a bunch of documents that you can observe. You know, there are words in it that you can read, but there's something going on in the background. Like, there are some underlying themes across these documents. And those themes are the latent variables that you want to extract. And that's the whole problem of topic modeling. One of the methods of doing that is latent Dirichlet allocation that we'll briefly present, and then you'll be able to apply it in your lab. Okay. So going back to the going back to the bag of words model for a second. If you think about it, like I mentioned, it gives you the relationship between documents and terms, right? You can also visualize it graphically, having a set of documents, a set of terms, and the matrix that you had, you know, was pointing out the relationships between these documents and terms. And I've loosely coded these lines as thicker or thinner. You can think of them as the different weights. You know, you could have a higher weightage if that term occurs more frequently in that document, etc. Does this make sense, a graphical representation? What we want to do in topic modeling is to first look at this setup and just think about it. If you have, I don't know, 500 documents and maybe 1,000 possible terms, 1,000 unique terms, how big would your matrix be? How many elements would that have? Sorry? The question is, if you have 500 documents and 1,000 unique terms, then how big would your document term matrix be? 500,000, right? It's pretty simple. You'd need one column and one column for each word, one row for each document. So it's 500,000 different, numbers that you need to store, and that's, the information that you're having to process, right? Now, to simplify that, what we want to do is introduce a layer of latent variables, okay? And we first find the relationship between these documents and the latent variables, and then the relationship between these latent variables and the words, right? Now you might think, does this really make any difference? Well, now going back to that same example, say you have 500 documents and 1,000 words. Now you come up with, say, a very small number of topics, say 10 topics, right? Now how many numbers do you need to represent? Keep in mind that now since we've broken this down into two parts, we'll have two different matrices, two different relationships. One is between the documents and the latent variables, and the other between this and the words. So let's think about it. So first we have 500 documents and 10 topics. So that's 500 times 10, 5,000 different numbers. And then 10 times 1,000, that's 10,000 numbers. So a total of 15,000 numbers, right? So remember what we started with? We started with a big matrix of 500,000 numbers, and we broke it down into two much, much smaller matrices, 5,000, 10,000 for a total of 15,000 numbers. And you might think, so like what are we losing out in this? Yes, we are losing out something, but it's not necessarily bad. What's going on is by applying these topics, we are constraining the kind of relationships that we can have between documents and individual words, right? So if you had, I don't know, if you had texts from completely unrelated sources, which were talking about, a bunch of different things, then this sort of representation will actually lose out on a lot of information. But if your corpus is from a similar source, or for instance, it's a set of forum posts from a forum on a particular topic or in a subject area, then there are, there's a very high chance that there are common themes or common topics underlying. And there's actually a benefit to doing this, which is you're compressing down the information that you need to store for the model, and the other is you're actually able to extract useful topics or underlying themes from it. Yeah.
So, but does that improve the accuracy at all? It actually does, because you're actually reducing the dimensionality of your data.
Right.
So you're losing something as well, right? When
Yeah.
you do that, but you're saying that actually this would help you improve the accuracy?
Yes. So
given that you have infinite time and, assuming you know, but you have infinite time and resource.
right.
On the test set.
On a test set, yeah.
On the training set, you'll always reduce the accuracy.
You will reduce the accuracy on the training set because you're actually losing information, that's right. But what you're essentially doing in machine learning terms is you're preventing the model from overfitting on your training data, right? So if you had the original model going directly from documents to words, and you had a model which you set up somehow to predict, for instance, okay, here is a document ID, what are the words in it? And say you had, again, infinite time and computational resources, and you could, build the perfect model that can predict, given a document identifier or something, what words will be in it. As long as you give it something from the training set, say it does perfectly and it predicts them all correctly. What happens if you give it a new document or a new test for it to perform? It will come up with some answer, but that answer will be very, very highly dependent on the examples it has seen. And in general, you don't really want that. You want the model to be able to generalize to newer instances. You will actually want it to be able to find patterns in the data and not just mug up the data and reproduce it, right? And there is another spin to this. Some people will recognize this as matrix factorization, and that is another way of looking at it. It is exactly that. We started with a bigger matrix and we factorized it into two smaller matrices. And this is something that is common, that's done in other disciplines as well in order to model data more effectively. And this is just an example of how you would do it in the natural language processing domain. Yeah.
Is there any way to quantify the information loss because of the prediction of the latent variable?
That's a good question. Is there a way to quantify the information lost due to introducing these latent variables? It's one way of doing it is, say like I mentioned, you train a model to predict directly from documents to words. Then you train a model based on this decomposition, and then you compare how much difference there is between their accuracies on the training set. That's one way of measuring the loss, but it depends a lot on the nature of the actual documents. If your actual documents had these underlying topics in them, which is typically the case with a lot of common sources, then you would actually not have a whole lot of loss. For instance, this is a very abstract diagram, but just to give you an example, you could have topics like politics, sports, medicine. and maybe your documents are, news articles that are coming out, and, you will see that they do have these underlying themes going along. So, yeah.
Say it this way is that how you determine what the latent variables are.
How do you?
If I see this example, bar, food, jam, you can see as that latent variable is bar.
Could be. Yeah.
Because how you define the latent
Right.
variable and how you map it to the real variables.
That's a very, very good question. So how do you find what the latent variables are, right? The interesting thing is LDA will find those latent variables for you.
Who does, or who will be able to?
Like LDA, the process we're going to talk about, is going to find it. But it's not going to look like what you think, okay? It's not going to come out and say, the theme here is restaurant. What it will do is it'll come up with a combination of these words. So it'll say, here's a topic I found. The topic is 0.5 bar, 0.2 G, and 0.3 jam, right? And if you, as a human, you can then interpret it as, oh, this is talking about like food in general, or this is talking about politics. And you'll actually get to see this more when you do the lab.
Do you have to define the number of Z?
Yes, that's one thing that you have to define. Typically, we typically call this a hyperparameter. It's not something that the system is learning on its own. You're defining, but one thing you can do is, like the brute force approach, is to try a bunch of different Z's and see which one gives you a better result at the end. But yes, that's right. That's one parameter that you have to choose. All right. Sorry, I shouldn't skip the math. So another way of interpreting this diagram or these relationships is, let me keep this. Okay. So going from documents to topics, D to Z, what these lines signify, or what these numbers in the matrix signify, are basically the probability of this topic being a part of this document, PZ given D. Similarly, the relationship between topics and words signify what is the probability that this word is generated from this topic, or would be generated by this topic, right? And what this overall scheme is trying to capture is the probability that this word is belongs to or occurs in this document PT given D, and we basically broke it down into two separate probabilities. But if you look at it carefully, this is giving you, we're only talking about conditional probabilities here. So we don't have a prior on these, which means, you can figure out relatively how often these words occur in these documents, but you won't be able to get an absolute number on these probabilities. So that's, yeah.
Sorry, can you go back?
Oh, sorry, yeah.
No, not this one.
Next one, yeah.
Yeah. Okay, so
Mhm.
you have three groups, right? And just say you want to figure out which document is the most ideal representation of the group. Like you got 5 documents. So would you do it as like which one is the biggest weighting of one group, or would it be like you compare the biggest weighting of one group with the second weighting, like within the same document?
So you're trying to find out which
document best represents a group?
So say you're given a bunch of words, and you're trying to figure out which document that came from, or most
So
likely
the
came from.
3 in the middle, the orange, the blue, and the purple, right?
Yeah.
I want to know which document represents each of them the best. But there's 5 documents.
Right.
But I can only choose 3 of them. So how would you do it? Like,
So it's not really. So let me go back. The combination here is not really a binary thing. It's not like you have 5, and then you're choosing 3
Sure,
out
sure.
of them.
Yeah.
But these 3 are combinations of all 5.
So, for example, the first document might have weighting like the yellow one's like 0.5,
Right.
the blue one's 0.25,
Mm-hmm.
and the purple one's like 0.25, right?
Right. Yeah.
So just say the 0.5 is the biggest one across all the documents
Right.
for yellow. So would you say like the first one is the best representative of yellow, or would you say like no, it's the yellow compared to the blue of the first document?
That's a good question. Like, how do you interpret these different weightages, right?
Yeah.
Do you see them as, you know, this document as being a perfect example of a certain topic, a high example? Yes, you can interpret it that way if you want to, right? Typically, what you would do is, you know, for most natural language documents, you wouldn't have a very high weightage on one individual topic. Typically, you'll have a mixture. But yeah, what you could do is you could say, for instance, in this document collection, I want all the topics that score high on the politics scale or something, right? And you could use that as a threshold to then select a bunch of documents and say, oh, these are good examples of documents that talk about politics, or these talk about sports. So you could do that. But yeah, sorry, go ahead.
But we're not doing this manually, right? It's all done by the tool.
Yeah, so the analysis is done automatically. This identifying what are some good topics is done automatically. But then after that, how you utilize that information is up to you. So for instance, what you could do is you can use the weights on these documents as an input to another algorithm, right? For instance, say document 1 is like you said, 0.1 or 0.5 yellow, 0.1 blue, and 0.2 magenta or purple. That vector of 3 numbers can become a representation for this document, and you can feed it onto another system, right? So there are automated pipelines where you can put this in, or you can do a more manual analysis. Say you're processing a dense news feed and you want to identify articles about a certain topic area, then you can do it, filter those manually like that. So I'll touch on this briefly because there is a lot of probability and math involved here. Like I mentioned, so far we've only been looking at conditional probabilities, and the way to read this is, what is the probability of T given D? Which means, what are the chances of this word occurring given this document has been presented to you? So it's a relative probability. You know, you have to have something given to you, and then you're trying to compute the probability based on that event occurring. But what is the joint probability, or what is the total probability? In order to find that, we need priors. Like, what is the prior probability of this document occurring at all, or what is the prior probability of this topic occurring at all? And these are things that need to be sort of estimated, and this is where the Dirichlet distributions come in. It's a very involved topic. Not going to go into it a whole lot right now, but if you're interested, definitely look up. It's super fascinating. The whole idea is you need to have this mathematical basis so that your analysis is correct and gives you meaningful results. And the way the overall LDA, latent Dirichlet allocation framework, works is, for each document you have a set of words, W, and you want to estimate a certain number of topics, Z. So you find the relationships between the possible topics and the words. Where do you get these topics from? Well, one idea is you randomly initialize them, right? You randomly initialize, say, okay, here's a topic which is this combination of words. And you find the relationship between that and all individual documents. And then across documents, you look at a set of parameters, we call these theta, that generate those or that are related to those topics. Now these parameters will start encoding the documents themselves. And the way this whole procedure works is iteratively. It assumes, this is a good, let me come up with some random combination of topics, some random combination of document parameters, and see how well it fits the observed words. Okay, it's making mistakes here. Let me adjust it slightly. Let me adjust the weights a little bit so that it fits the given data better. And at the end of it, we also need to apply the priors we talked about, and the priors come from these Dirichlet distributions, which are a very very intuitive way of mapping out combinations of factors. So whenever you're talking about, okay, I have like 3 words, 3 words, and I want to create a topic out of that, then that topic can be a mixture of those words. For instance, I should come up with a more concrete example for this. Like sports, for instance, is the topic, and say you have 3 words called ball, sky, and I don't know, cloth, okay? And you start with a random initialization. So you say, let's assume this topic sport is 0.1 ball, 0.2 sky, and 0.5 cloth, right? But how do you come up with these numbers? If you sample them from a Dirichlet distribution, then it ensures that all those numbers add up to 1, okay? And there are parameters using which you can tweak the Dirichlet distribution so that it either produces very mixed numbers or it produces very skewed numbers. So skewed numbers would be where one of the topics is very high and the others are low, whereas more mixed numbers would be things that are closer to each other. Okay, that's where the Dirichlet distributions come in. You start picking from there and you iteratively optimize it. And the use cases for this sort of approach, you can analyze the underlying topics and then use that information to categorize documents. You can, given a new document, you can figure out what mixture of topics is there, so that might be useful to you. You can also generate collections of words. So, for instance, you could generate a new document using this form, just working backwards. Like, you apply those same probabilities backwards to generate a collection of words, call it a document. They won't be in proper grammatical order, but they might give you a sense of, okay, this is what this topic area sounds like. And then I have a little bit more on LDA, but I feel like the time is ripe for getting into the lab. I'll leave this on for a second. The idea is to quickly summarize what the LDA process looks like. As we heard before, let's choose a number of topics that we want to identify, initialize the distribution parameters, and the parameters there, as I mentioned briefly, you can tweak whether you want more mixed topics or more skewed topics, and then you sample a bunch of documents and words. You see if those, if the distribution parameters actually fit the observed documents and words, and then you update the distributions according to that. And you keep iterating till you reach some level of convergence. And then the result that you get is your mixture of topics. And this is, you can think of it as a form of expectation maximization, which is another common technique in machine learning. So, like I mentioned, if you're interested in this, there are additional resources. By the way, the slides are also there in the repo, so you'll be able to find links to these. So, any questions so far on LDA? Yeah.
So the Dirichlet distribution
Mhm.
helps us initialize the parameters, and then the iterative process takes over.
Pretty much. There is something more there. the idea is when you're performing these updates, the fact that you sample these numbers from a Dirichlet distribution can help you with how you make those updates. So it's kind of related to, like in neural networks, if you're applying an activation function, and we'll get to some of this later on, knowing what activation function you had applied can help you then further optimize. Or in a more statistical modeling scenario, if you can assume that these numbers are coming from a certain distribution, like a normal distribution, then you know certain properties of it, and so you can optimize your algorithm accordingly. So that's one of the reasons we set the distribution like that. But a lot of this will become clearer as you apply it yourself. Like, there's no use me just talking through it. So we can, jump into the lab, and the lab is basically going to be a Jupyter notebook where you go through and take a data set and perform LDA topic modeling on it. And Adarsh is going to lead this portion.
Yeah, so the lab today, the objective is to implement LDA. You can use this lab for your own use case. One of the big things I like to tell people is that any algorithm you use, you want to make sure that the use case is applicable, and you might have to tweak parameters based on whatever problem it is you're trying to solve. So today what we're going to do is we're actually going to use a data set that's called the news group data set. So back in the 90s, there used to be this online forum. I'm sure some of you know this, but for folks that don't, it's basically kind of similar to Reddit. Folks would go online, talk about stuff. It was basically a forum. You could sign in. There were various classifications, and so they had various different topic areas, and you could go in and you could find like-minded people and talk about stuff. So this data set is pretty large. It has about 20 different categories. But a lot of these categories are actually very similarly correlated. So for example, politics has 5 subcategories. Like politics has the Middle East, there's government, science had a bunch of categories, space, physics, stuff like that. So even though it's 20 different categories, it's more or less like maybe 10 or 12. And so our objective here is basically we're going to take this data set, which has all of this forum data, right? And it's in some way, in some sense, it's already bunched into various different categories, so we know that. So I'll actually get into like the Dirichlet and the latent part of what the algorithm does. So if you want to think of what a Dirichlet distribution looks like, if you want to think about it in a 3D space, you can think of it as kind of a graph that has hills, and each of these hills are various local maximas. And each of these local maximas are each of our topic areas. And this works great for forum categories. It works great for Wikipedia articles because a lot of these articles are kind of siloed in some kind of bigger category. So politics would be one, sports would be one, education would be one, math, science, all that good stuff. So what we're going to do here is we're going to run a flavor of LDA, and we're going to try and get these categories based on studying the newsgroup data. So one thing to note is that, generally speaking, you asked a question of how do you know how many categories there are? So that's where the use case and the domain expertise comes in. If you have a forum and there's like 30 different topic areas, okay, so there's 30 different categories. I don't know what the new topics or the new text coming in, I don't know where it belongs, but I do know that generally speaking, there's 30 different topic areas, and it's probably going to be one of them. So LDA, essentially what it does is, it builds a topic per document model and a words per topic model. So it's documents, topics, and words. And each of those is essentially on top of each other, and that's kind of how you build this. So I'm going to go through all the steps, from start to finish. We'll be training this both on the bag of words model. We'll also be doing this on the TF-IDF model. And then we feed that into LDA, and then we're going to get the categories, and then right at the end, what we're also going to do is we're going to generate some text. So I'll be typing in some text, And then I'm going to ask my model to tell me, okay, which category does this belong to? So start to finish, we're going to go through every step. So step one, so we load our data sets. So the good thing about the NewsDrip data set is that it comes preloaded with sklearn. You can see some information about the data set here. So as you can see, we have various different categories. I mentioned like politics has guns, it has Middle East, recreational has autos, motorcycles. For science, there's electronics, medical, science, space, etc. So it's a really great data set if you want to run topic modeling. It's a really great data set if you want to run any kind of text processing, really, because it's more or less pretty clean and it's vast. So it's really useful for testing how good your model is. So, so first step is, really I set my random seed so it's reproducible. I save my documents in a documents variable. I remove the headers, footers, and the quotes just so that it's cleaner. I don't want, any of the actual like forum headers. We have about 11,000 documents, as you can see, so it's pretty big. It's pretty large. So what we're going to do is, before I even get into step 2 and before I get into the data preprocessing section, I'm going to take one of these documents, which I'm calling document num 4310, which is just a random document, and I'm going to use this to really test how well my model is doing it. And you'll see at the end of the lab how we actually use this. So, for example, I'm previewing this document over here, and it says, fret not, you made it. Hey, gang, it's not about duck hunting or dark alleys. It's about black-clad, helmeted, booted troops storming into houses and violating civil rights. Are you ready to defend your constitution? So clearly, this person is very passionate about, I guess, owning guns. And so you could read this and think, okay, this document could come under politics. I don't know. But if at the end of the day, if our model is able to classify this into a topic that's... Increase the font size? Sure. Is that better? Even more? Is that better? A little more? Okay. Is that better? All right. Okay, so yeah, so at this point we know that, all right, so it looks like this could come under politics. We don't know, but we're going to test it at the end just to see that, it actually works out that way.
I'm sorry, the politics is, that's part of do the documents come with a label? Or?
No. So politics is my assumption. So Arpan mentioned, so actually this is a good point for me to bring up. So in LDA, there's a word latent, right? And so latent in statistics really means that it's something that you don't observe, it's something that you have to infer. So the latent in LDA, in our particular use case, is we have to figure out what these categories are. LDA is not going to come and tell you this category is politics. But what it will tell you is it will give you a bunch of words with weights attached to them that are somewhat similar and fall under a specific category.
This is unsupervised learning.
Yes. This is unsupervised learning. This is an unsupervised learning problem where we are inferring what the category is. We don't know what it is. So I'm assuming... I'm sorry? Yes, so I mentioned the Dirichlet prior. So basically in a graph, in a 3D graph, these are local maximas and each local maxima corresponds to a specific topic. You don't know what the name of the topic is, that's what you're going to infer. But you can think of it like in a 3D graph, it's like hills, right? But you kind of put that on a plane and not in a 2D space. So that's kind of what it looks like. So I'm simply saying this could be politics, it could be about guns, I don't know, but it's somewhat in that space. So data preprocessing, Arpan mentioned all of these steps. So the first step is tokenization. It's pretty standard. You really want to take your text and you want to split it up. You want to make sure that you're considering each word for what it is and not having multiple combinations of the same word. So if you have a word that has capitalization or if it's got things attached to the word, you don't want to assume that those are two different words. It is the same word. All the stop words are removed. So Arpan mentioned this as well. These are words that are basically like very common words. Like articles, and the words that don't really contribute to the actual meaning. So you want to get rid of them as well. Lemmatization, generally speaking, it's words that you want to change them to their present tense, and so you don't want to have multiple words in different tenses, and you don't want to account for them to be individual words. You want to bring all of them to present tense, and so they're unique. And stemming is essentially reducing it to its root form. So went will become go. Like went is the future tense, or like the past, yes, it's a past tense of go. So that's what stemming would be. So in the repo, you'll see that I use, in the requirements.txt file, you will see gensim. So you want to install gensim. Gensim is really great for topic modeling, text processing. There's a lot of really, it's open source, so you can actually go in and see what the code does. It's got a lot of libraries that you can use to take care of all the pre-processing steps. NLTK as well. Most of you might know about this. It's got lemmatization, stemmer libraries that you can use. Generally speaking, for text processing and NLP projects, NLTK, gensim are very, very useful. Highly recommend using them. If you don't have them, and if you're doing this right now on your computer, and you shouldn't have to do this, but if you do this and you actually want a copy of it, you can uncomment these lines and you will have them. So here I have a couple examples of what lemmatization is. And so as you can see, went becomes go. And essentially it's past tense to present tense. A stemming example here, I've got a bunch of words. And really what it's doing is it's taking the word and reducing it to its root form. So caresses becomes caress, flies becomes fly. And as you can see, like you can actually put in more words here and you can see what the root form is. So you can actually play around with this and see what it does. In the data preprocessing tab over here, it's just like two helper functions. It's essentially the same thing that we did over here, except I'm putting them into a function, and so I can actually run my entire corpus on this. Essentially if you look at what I'm actually doing, so the lemmatized stemming, what it does is it lemmatizes all the words, and then in the pre-processing function, what I'm doing is I'm removing stop words, and I'm also removing words that are less than 3 characters long. And then I'm gonna use these functions later in the project. So going back to our test document, so 4310 was the document ID I used at the start. This is what it looks like, the original document. And what I'm doing here is I'm pre-processing that specific document. So documents is my entire corpus. Document num is 4310. So I'm pre-processing that entire corpus using my helper function that I've defined over here. And once I do that, essentially my document goes from that to this. So as you can see, it takes care of all the pre-processing steps. It tokenizes them, lemmatizes them, stems them, and I get a much cleaner, more pure form of what the actual text is trying to do. And then in this step, I actually do this for the entire corpus. If you're running this on your system, this might take a few minutes. It's a pretty large corpus. So just one thing you want to keep in mind. So bag of words. So the bag of words model, as Arpan described, it's a frequency term distribution matrix. Very simple. The words are the columns. So every word, you count how many times it appears. And that's basically what it is. And it's a bag of words that you take and you convert it into a matrix. So in this project, what we're going to do is we're actually going to run LDA both on bag of words and on TF-IDF. So, and you're going to see, we actually get a better result with bag of words. Long story short, when you're applying TF-IDF and bag of words, and if you're thinking about which one you should apply, I'd recommend applying both, really, because it really comes down to the use case. TF-IDF, I'll go a little bit into TF-IDF as well and what it actually does. But TF-IDF can result in loss of information because it kind of leans towards focusing on nouns. And bag of words, although you lose a lot of the context, in some use cases, it can actually grab the essence of the information better than TF-IDF. So we're going to do both, and you'll see the results at the end of the project. So I'm creating a dictionary, which is a key value pair for all my pre-processed documents. And once I have my dictionary, essentially what I'm going to do is I'm going to do a little bit more pre-processing, which, again, these particular steps, it really comes down to your data set. So if your data set does not warrant removing certain pieces of information, you should not do that. But for news groups, it makes sense.
They added this to TF idea
Mhm.
that is trying to emphasize the different words which are occurring only in some documents get higher weightage, but the words which occur in many, many documents get a lower weightage.
Yes.
Where does this loss of information that is going to happen? When you say TF-IDF is lost.
Yeah. So TF-IDF, like you mentioned, if a word occurs many times in one document, if you look at it just in that perspective, it probably makes sense. Okay, this word it's 20 times in this particular document, probably this document's about that word. But if that same word occurs across all documents, then you kind of weight it down. And so really what it comes down to is TF-IDF, generally speaking, starts to pick up nouns. And so if your corpus of text has a general tendency to deal with a lot of words that are nouns and that are unique in that sense, TF-IDF works very well. But if you're dealing with forum data, if you're dealing with text data that's very user conversation based, TF-IDF does not do very well. So if you and I are having a conversation, right, and it's kind of like we're chatting with each other, we're not going to use as much of, or I should say, we're not going to have as many nouns as we would use if it was a more formal conversation. So generally speaking, if the conversation is text and chat based, you'd want to not use TF-IDF. But it also depends on how large your corpus of text is. So TF-IDF can lose some of the conversational pieces of what is uniquely identifying that piece of text. Yeah.
Do you want to avoid stemming or lemmatization for the same reason in that case?
I'm sorry?
Would you want to avoid lemmatization stemming?
Yeah. So again, stemming and lemmatization it's not something that you always have to do. Tokenization, I'd recommend yes. Stemming and lemmatization, you may not always want to apply because, again, you could lose a lot of information. So at the end of the day, when it comes to something like LDA, you're already dealing with loss of information. You're dealing with really trying to grab some essence out of all of these documents. So basically, you either do stemming and lemmatization before your bag of words. If you're not getting a good result, I'd recommend not doing that. Directly applying a bag of words, removing stop words, and then going ahead with it. So it's not a rule that you have to stemmatize and lemmatize right before. Right. So what I'm doing here is, yeah. So this is another pre-processing step where essentially what I'm doing is I'm filtering out the extremes. So in this specific step, all words that appear less than 15 times in a document, I'm getting rid of them, and all the words appearing more than 10% in all documents, I'm getting rid of them as well. So basically what I'm doing is, if I have a dictionary and I have like 6 million words, I want to consider not the outliers, but the words that are kind of in between. These numbers and percentages, there's no hard and fast rule. You could use a grid search, you could run a parameter-based grid search and kind of optimize on this. But for this particular data set, this works out pretty well. Usually, the words appearing in more than 10% of documents, folks like to use 20%, 25% if you really want to get down to the brass tacks of it. But this corpus of text is not that big. It's about 11,000 documents, so I've kept it at about 10%. Dr. Bao. So this is the next step where basically what we're doing is we're taking our pre-processed documents, and I am now going to convert that into a bag of words. So Dr. Bao is a library that I'm using, so for doc and process documents, which is my process documents, I am converting it into a bag of words. And I'll show you what the bag of words looks like. So essentially for our test document, which I've been using throughout 4310, it basically outputs a tuple, a list with a bunch of sets in them. So it's token ID and the token count. And the token ID is the ID of the word in my whole vocabulary. So this is what 4310, so the document we had above about guns, this is what that looks like in a bag of words converted model. In this particular step, I'm doing basically the same thing, but I wanted to show you actually what each word is. So you saw the token ID, you saw the token count. What I'm doing here is I'm showing you the token ID is this word and that appears these many times. So as you saw, so up here was 146 and 1. So in this step, all I'm doing is I'm saying the word 146, which is color, appears one time. And then I go through each word. So now you can see that we've taken our document and we have the ID, we have the word, and we have the count. So TF-IDF on our documents. And so at the end of this step, I essentially run that overall on my entire vocabulary, and I get a bag of words model. Now I'm going to do a very similar process and convert it into a TF-IDF. Once I have my bag of word corpus, once I have my TF-IDF corpus, I'm then going to apply that into LDA, and then we're going to take a look at what topics we actually see. So Arpan mentioned a little bit about TF-IDF, which is transform, term frequency, inverse document frequency. So generally speaking, right, I just mentioned that to that sort over there. If a word appears many times in one document, it's probably important. But if that word appears many times in several or all documents, you want to weight that down. And that's where TF-IDF comes in. So to give you an example, right? So let's say that we have a document containing 100 words, and the word tiger appears 3 times. So the term frequency of that particular document is so I have the formula up here, the number of times that word appears in that document divided by the total number of terms in that document. So we have a document with 100 words, tiger appears 3 times, term frequency is 3 divided by 100. Now, let's assume that in our entire corpus, we have 10 million documents. And in this entire 10 million document corpus, the word tiger appears 1,000 times. So I'm first looking at individual document, and now I'm looking at the entire corpus. So in the individual document, tiger appears 3 times. In the entire corpus, it appears 1,000 times. So my inverse document frequency is the total number of documents, which is 10 million. So that's my numerator. And the number of documents with the term tiger in it, which is 1,000. So my IDF value is the log of 10 million, which is the total number, and 1,000, which is the number of times it appears, which is 4. And the TF-IDF weight for that particular word, for that corpus, is the multiplication of these two values. So it's 0.12. And that's a very layman explanation of how the TF-IDF value is calculated. So going back into my GenSim corpus, what I do is I import TF-IDF. I save my model into a TF-IDF variable. I'm then applying my TF-IDF model, and I'm calling it corpus TF-IDF. So basically, initially you saw token ID and token count. Now what you're going to see is token ID and TF-IDF value. So it's very similar to the bag of words in terms of like what the actual final representation looks like, but the count values are not frequency distributions. They're weights. And that's why you can actually take bag of words, you can take TF-IDF, and then you can apply different models on it and actually see how well it's doing for both. So, so in step 4, what we're going to do is now we have our bag of words corpus, we have our LDA corpus, we have our TF-IDF corpus, and now we're going to actually apply LDA to both of these. My general assumption, so the assumption that I have going at the start, Dan, he mentioned the question earlier, but how many topics I have, I'm putting it as 10. So what I did was basically, I went into the NewsGrid data set, looked at all the categories, and I saw that, okay, generally speaking, there's about 10 categories here. If you want to get more granular results, you'd have to run this for a longer amount of time. So I ran this for about 30 minutes or so, 25 to 30 minutes. I got results that worked, but if you want to try this at home, and you actually want to get all 20 newsgroup categories, I'd recommend actually running this for much longer. So I'll get into passes and what that means and how you can actually make it work that way. So just for the purposes of this, let's go with 10 categories. So some of the parameters that we're going to be playing with in LDA are as follows. So num topics is the number of requested latent topics. So the reason I say latent topics, again, is because we have to infer these. LDA is not going to tell me what these categories are. It's not an observation, it's an inference. And when you have an inference, it becomes latent. ID to word is just the mapping of word IDs to the actual word, which is our dictionary, which we defined earlier. Workers is the number of extra processes if you want to use parallelization. So generally speaking, right? So if you have an Intel Core i7, you have, I think, 4 processors. And generally speaking, if you want to run this on your system and you have a lot of memory, you want to specify it as one less than the number of processors you have. So if you have an i7, I'd recommend 3. The default, so if you don't set a value for this, it'll use all of your cores, which is fine, but your system may crash. So just keep that in mind. If you're not sure how many cores you have, set it at S2, it'll work just fine. So alpha and ETA. So alpha and eta are the 2 hyperparameters that are key in this. So in the diagram that Arpan mentioned, these are the theta and lambda values. So essentially what alpha and ETA tells you is if every document has a mixture of many topics, which means it's kind of dirty, right? Generally speaking, what you want is if a document comes from a specific category, you don't want that document to have random conversations, or that document should talk about sports and politics and the military and all of that in one specific document. For those kinds of cases, or if that's the kind of text you're dealing with, the alpha value that you're setting, which is your dirichlet prior, should be a higher value. So that's basically what alpha is. Default value is 1 divided by the number of topics you set. So for our case, it's 0.1. So ETA is the per topic word distribution. So basically, if each topic has a mixture of many different kinds of words, so again, this is not what we want, because if topics are not uniquely identifiable, then that's a problem. So if you have like a document that has a mixture of a lot of topics, you have a high alpha value. If you have a topic that has a mixture of a lot of words, you have a high eta value. So these are 2 parameters that you will be setting. So the data set we're using is pretty clean in that sense. Generally speaking, these values, I would not set ad hominem. I would run a grid search for sure. I'd start with the default value, which is 1 divided by the number of topics you have, and then kind of take it from there. But if you can apply your domain expertise based on the kind of text you're getting, you can then put some intuition and set a high alpha value or set a low alpha value, or the same thing for the ETA value. Passes. So passes is the number of training passes through the corpus. So this is a very important parameter. I've done this notebook and the entire analysis with 50 passes. To give you an idea of what one pass is, so for example, if the training corpus has 50,000 documents, so you have 50,000 documents and you have a chunk size of 10,000 documents, and you have 2 passes, that means training is done in 10 updates. So you have 50,000 documents, your chunk size is 10, so it's going to run through 50,000 5 times, and if you have 2 passes overall, you're actually going to do that again. So you have 10 updates. Make sense? All right, so 50,000 documents, chunk size of 10,000, it's going to take 5 passes or 5 updates for the first run. That's the first pass. The second pass will do the exact same thing, 50,000 documents, 10,000 documents at a time. So it's a total of 10 updates with 2 passes. So what I'm doing over here is I'm actually doing this with 50 passes. So that's why if you're trying to run it, it'll take about 30 to 40 minutes. You could reduce your number of passes to 5 or 10, but you're going to get garbage topics. So it's garbage in, garbage out. LD is an iterative model. The more number of passes, the better. The more it'll be able to actually infer from the actual text. So setting the right passes values is key in this case. Again, you don't want to set these ad hominem. Grid search is the best way to do this. Yeah. So generally speaking, you want to start at 50, 75 passes. That's what I've been doing. It works fine. If it's still not working with those values, it's probably not to do with the number of passes, and it's probably got more to do with your alpha and eta values. So whatever grid search you're running, you want to make sure that the passes, the alpha values, and the ETA values are all going through that grid search in a combination that allows you to get to a final conclusion point that makes sense for all. So that's how you'd want to do it. So this is where I'm actually training the models. So my BOW corpus is the bag of words corpus. I've got 10 topics. My ID2 word is the dictionary that I defined earlier. 50 passes, and I'm using two workers, which is 2 cores. You can also do this using monocore. I've got that up, right above that. The only difference is that that does not have workers. So it's using 1 core. It's going to be way slower, just so you know. So once I have my LDA model defined and it's trained and it's actually gone through my entire corpus of text, what I'm doing here is I'm actually printing out what these topics are. So I'm actually going to zoom out a little bit here because there's quite a few. All right, so essentially what this is telling me is I've run my LDA model on my entire corpus of text, and this is the output that I get. So as you can see, it does not tell me what the topic is. So if you see it's topic, and then I get, so it's topic 0, topic 1, topic 2, topic 3. I've got 10 topics. And for each topic, it tells me what are the words associated with that topic that have the highest weights. You can print out all the words. They will all sum to 1. I'm printing out just the top 10. And so going through our analysis, right? So we have reached a point where now my model is telling me that these are the various topics I have. Now let's take a look at some of these words, right? So topic 0 has file, window, program, software, server, could be computer software. Let's see, topic 4 has game, team, play, player, season, hockey, league, probably sports. Topic 6 has Christian, church, Jesus, Bible, book, faith, probably about religion. Topic 8 has bike, drive, engine, probably automobiles, right? Topic 9 has govern, firearm, Armenian, state, kill, Turkish, attack, children, probably government or something of that sort, right? So to answer your question, right? The latent part of this algorithm is now you have to come up with what these categories are. LD is going to tell you these are the words associated with this topic, and now I have, generally speaking, some idea of what each topic actually points to. And so what I've done here is I've actually gone ahead and given some of these names. So I've said, okay, so 0 was computer software, 4 was sports, 6 was religion, 9 was politics, 8 was automotives. Like topic 1 is space, encrypt, technology, govern, public. So when you have space, govern, and public in the same one, it's probably NASA, right? It's something to do with space. So these values are going to change based on how much time you give your algorithm and how many passes you allow it to actually do. So I'm able to come up with 10 classifications based on the topics that I have. My next step is I'm going to do this exact same thing.
So what is the absolute, what is interpretation of the absolute value for those weights? Like, they don't add up to 1, so.
No, so I'm printing out 10 words. You can print out all the words and they will add up to 1. So you can select the top 5 words for each topic, top 10, top 20. So these weights will add up to 1, but they're going to be a large number of weights because it's 11,000 documents. My frequency term distribution matrix is going to have millions of columns. You're going to have a lot of words in there. So usually as you go further and further south, it's going to be very, very small weights. So it doesn't make any sense to actually go that deep. So if you don't get your category in the first 10, 20 words, you're probably doing something wrong. Yeah. So I'm going to do this exact same thing using TF-IDF as well. So it's a very similar process. I define my corpus TF-IDF because that's the pre-processing we did a little earlier. I define 10 topics. My dictionary is the ID to word. I have 50 passes, 4 workers. And very, very interestingly, the output I got with TF-IDF was not as good.
Can you go back to your topic on the time? So how do you know that, the grouping, yeah. How do you know that your pass is correct, the number of passes you have done? Because you find the similarity between those, that's how you say it's correct?
So how do you know if the number of passes is right? How do you know if your alpha values are right? Or how do you know if your ETA values are right? Generally speaking, in an unsupervised learning problem, you will never know 100%. Like I even if I'm applying this to my work, I will go and tell my boss, I'm sure about this, but I'm not 100%. Because what we're trying to do here is optimize for something that is basically usually done by a human being, right? So if you're working at Comcast, right, you get thousands of emails through customer support every day. There's probably someone sitting there at the front line that assigns tickets to various teams, right? So if it could be about Comcast internet, it could be about Comcast cable, it could be about Comcast fiber optics. So this human being is assigning tickets to then the right team. Theoretically speaking, you could automate that process by using an LDA model where it is able to read what's in the actual email. You have a general idea of how many topic areas you have, and it'll then direct it automatically. Are you going to have false positives? For sure. Yeah. All right. So, yeah. Yeah. Sure. Anyone.
So on the groupings, are the words being grouped by proximity to sort of central cluster in that?
Yeah. Yes.
Piggybacking off the question, so is there something like roughly comparable to like silhouette scoring?
Yes. So I'm actually going to come to a metric right at the end. So we use log perplexity, which is it's a measure of entropy. For this kind of problem, when you're actually trying to quantify how well it's doing, using something like perplexity is as close to a metric as you can get. So generally speaking, so log perplexity is the log likelihood of your model being able to generate the text for that specific topic. And the lower the value, the better your model is doing. But what I would do is basically set a benchmark on the perplexity metric and then iterate over how well that's doing based on the use cases that you have. So if you're able to get, a certain amount of accuracy or a certain amount of like true positive, true negative rate, using the perplexity value that's assigned to that specific metric, that specific example first, and then you then kind of optimize on that. So there's no like hard and fast, yes, it's doing well. Perplexity, which is a measure of entropy, is your best bet for this. Yeah. So what I'm doing, so over here is the exact same thing. I'm now applying it to TF-IDF. Yeah.
One digression, but is there a way of looking at it in the supervised classification sense in the following manner? If someone were to give you 1,000 documents of type sports, another 1,000 of type environment, and so on and so forth, then running this and identifying which words represent those named topics is one way to go.
Yes.
Now it's a supervised.
Yes, so you can very easily transfer this into a supervised learning setting as well. So one thing I like to do is, so basically, if I'm hired by a company and I don't know what the topics are, right? And I don't know anything about what the actual text is or what it means, you could theoretically use transfer learning, figure out the topics you have, and then use that as a basis for a supervised learning classification problem where then every piece of text coming in goes into that specific topic. So yes, you could use this as a precursor step to identify what you want to classify later. Yeah, true. So I run this on TF-IDF. So with TF-IDF, right, I was able to run this and I was not able to actually come up with categories for each of them. So I spent some time looking at this, and the solution probably is you want to run this for some more time, you want to give it more passes, but I was able to get very similar classifications, but I was not able to classify all of them. So if you look at the notebook, I've got a few unclears there. So, if topic 1, I see Windows, software, file, disk, monitor, probably computer software. I see Christian, religion, moral, Jesus, probably, something to do with religion, I guess. Let's look at topic number 5 and 6. So 5 and 6 is Gordon, patient, intellect, surrender, chastity. I'm not sure what that is. So you are going to, run into this where you just don't know what that means. And also, generally speaking, you will see that a lot of these words are nouns. So remember I told you earlier about TF-IDF putting more weights for nouns. So look at topic number 9, for example. It's Boston, Brave, Detroit, Chicago, baseball season. It's all nouns. So based on what kind of text you have and what the actual context is, if you have text that's noun heavy and it's more formal, usually TF-IDF is better. But because this is forum data, a lot of the context is in text that does not have that direct noun heaviness, which is why you don't really get to some kind of conclusion. So for example, if I look at topic number 8, I see motorcycle, I see Honda, so that's definitely automobiles. Let's look at topic number, what's another unclear one? Topic number 0. So detector, Adam, captain, ESPN, devil. ranger and lamp. I don't know. It doesn't make sense to me. So in this kind of situation, you either set up the grid search, like I said. So, the reason why I also added this is because this can sometimes not work. You have to really think about what kind of text you have, what your grid search looks like, and then take it from there. So TF-IDF in this particular case, I was able to get, some topics, but I was not able to classify all of them. So, so now what I want to do is so we separated out a document at the start of this lab, right? We separated out 4310, which was this individual talking about defending their constitution with guns, right? So we have that document, and now what I want to do is I really want to see where would that come under. So if my model is working right, again, in the perfect world, you'd want to use a new piece of text, which I have right at the end. So there's a little bit of a miscalculation here, but you should be able to write up a new piece of text, feed it to your model, and then your model should be able to tell you which topic it actually goes to, which I'll show you right at the end. So I have my text over here. Fret not, you made it. Not while we still have guns. Are you ready to defend your constitution? So what I'm doing is I'm feeding this back into my model, and then I'm actually figuring out, give me the top percentages or the top probabilities of which topic this could fall under. And it tells me that, it gives me 4 options, so it doesn't even account for the other 6. And these probabilities will sum to 1. So it tells me with 64.5% that it is under Armenian state, firearm, report, attack, children. And if I want to look at what that was, that is, I believe, politics, it should be. Yes, Armenian state, kill, firearm, attack, children. So what this is telling me that with a 64.5% chance that the text that we separated out earlier is in that specific category. And then I have 14.69%, 8%, which doesn't really account for anything. I'm then going to do this exact same example using my TF-IDF model to see, okay, what does my TF-IDF model tell me where this piece of text falls in? I do the same thing. Interestingly, it tells me with 34% chance that it falls under this category over here, which was politics. So if you go back and look at my TF-IDF topics, govern, encrypt, state, team, player, game, I don't know. Is it politics? But 46, so essentially like the percentage is lower. It's not as high as my bag of words. And that's my point in this case, because Armenian, Israel, Turkish, Turkey, Greek, Turk, it doesn't have to be politics, but this sounds like a mixture of Middle Eastern countries. What does that mean? I don't know. But what my TF-IDF model is telling me that it's telling me that with the 46% chance, it's probably something to do with this. So if you compare the two, for this particular use case, bag of words actually does better because it's a high percentage. This is where I was to answer your question about the log perplexity. So generally speaking, for unsupervised problems where you don't have a metric, entropy is something that you could use, which is a loss of information that you have. And the log likelihood for my model using my bag of words is minus 7.37. So the lower the value here, so generally speaking, the lower the value here, the better. I take this with a grain of salt. I don't really use the log perplexity metric. I try to have more of an eye test, and I try to use more examples and test cases to actually see how well my model is doing. But if you would like to, generally speaking, have a metric, the log perplexity is the way to go. And in my last and final step, what I'm doing is I'm going to take an unseen document, and I'm then going to feed it into my LDA model, which I've saved as a pickle, and I want it to tell me which category it falls under. And my sentence is, my favorite sports activities are running and swimming. Very clearly sports. I run it in. It tells me with a 61.69% that it falls under the topic that has game, team, play, player, and season, which was my sports category, which I defined earlier. So in about 30 minutes of processing and about 12,000 documents as my vocabulary, I'm able to train my model, and it can tell me with more than 50%, so with an over 60% chance that this piece of text is under this category. The assumptions, just to recap, you want to make sure that the model takes the assumptions that the text coming in has the Dirichlet priors, which are local maximas, with each local maxima being an actual topic area. You feed your text in with those classifications and those parameters set in. More often than not, you will be able to get a classification at the end of it in an unsupervised setting that your model will be able to tell you that, okay, this piece of text comes under this category. And yeah, that's the end of the lab.
So these topics are like open to interpretation.
Yes.
For example, in this Armenian Turkish one, you interpret it as politics. But
Yes.
it could be something else as well. Like it could be, say for example, genocide.
Yes.
Armenian genocide.
Mm-hmm.
So it could be history.
Yes.
As well. So it's like still open to interpretation.
So that's where the latent comes in. So the latent aspect of this is where it's inference. You have to infer what these topic areas are, which is why it's crucial that you actually run this, with the grid search over some time. Because if you go back and you look at the newsgroup articles, right? If you look at the newsgroup categorizations, they have a specific category that's politics, Middle East, and that's what that is. The reason why I didn't run it for 20 categories is because it would take about an hour and a half or so, and it would take a long time. So what I did was I basically condensed all of the politics topics into one politics. So Middle East, guns, government, all that stuff is politics. And so I'm able to see, okay, I see Armenia, all these countries. It's probably something to do with the government because like the word govern is there as well. So that's how I come up with, this is politics, because I know what the subclassifications are.
So it depends upon the context and
Yes.
how specific you want to be.
Yes, yes.
Is there functionality that would output what document is stored as which topic easily? I mean, I guess you can look it up.
Yeah. So if you want to look at which document is, yes, you could.
So I mean, it would be nice to just say, well, can you just give me a document number
Mhm.
of everything under Armenian?
Yeah. If you look at my actual code, there is a variable called document num. You can change that to whatever you'd like. And you can underscore num. So document num is the name of the variable, which I have set it as 4310 right at the start, which is, like I mentioned, I'm going to use that as an example. And so you can change that value and you can get the classifications for every single document. Yeah.
So for foreign language documents, ignoring my impression is that nothing within LDA sort of biases it towards English. Is that like a
So foreign language is a little tricky because one, you need to, it would help if you can speak that language and you can kind of understand what the impact of removing stop words, for example, is. Because some languages don't really use grammar, for example. It's just mostly, nouns, pronouns, verbs, adverbs. So you don't always want to do that. It's very specific to what language you're using for sure. So I haven't run this on other languages, but my guess would be that you would not stamatize and lamatize as a blanket rule for sure.
But nothing within LDA itself should generalize. Ignore, like that would be a preprocessing step when you describe.
Yes. No, LDA does not. No.
You mentioned this like grid search, right?
Yeah, grid search, yeah.
Can you describe it?
So grid search, okay, so let me visualize. So imagine you have a huge board and there's levers, right? And you have different rows and you tweak one lever, you tweak another level, and you tweak another one. That's one setting. Now, I want to do a combination of all of these levers. That's what a grid search is. So what I'm going to do is I'm going to take my model, I'm going to tweak my parameters, which is each of these values, and I'm going to try all the various different combinations. I will have a metric at the end which I decide, and I will try to optimize for that metric. So if I can run a grid search on all of my levers, which are my parameters, and whatever the value that I get, the highest value or the lowest value, I then pick that. So generally speaking, a grid search is a dictionary of values that have a whole range of combinations, and you want to be able to identify which combination of these values works best for your specific use case.
Can you use like cascaded LDA to identify subtleties in certain topics?
Yeah, so there's a thing called hierarchical LDA, which you can use for subcategories, yeah. All right, so we can take a break. After this, Luis is gonna go into deep neural networks. But yeah, thank you.
Okay, so we're going to start the second session. I'm too hyper for a microphone, but if I talk like this, can you all hear me? Yes? Cool. So, okay, well, thank you for sticking around. So the first part was a lot of NLP. The second part, we get to a point where we need to start using deep learning to get better results. So this part is going to be as follows. I'm going to give you an introduction to neural networks. Then we're going to do one lab that is about IMDb reviews, so movie reviews, sentiment analysis. Then we'll learn recurrent neural networks, and then we'll do a better a lab with the same data, but that does better using recurrent neural networks. Okay. So I'll start with a question. How many people know neural networks? Have seen them? Have worked a lot of people? Educated crowd. That's good. If you haven't seen them, don't worry. This is a cartoonish introduction to neural networks. Okay. And if you've seen them, I hope this shows it done to you in a different light. There'll be no formula, just cartoonish stuff. Anyway, so let me start with a question. And aside from NLP, obviously, what's your favorite application of neural networks? Maybe somebody can throw in some up there for work or
Image classification.
what classification?
Image classification.
Email classification, spam, etc.
Image.
Oh, image, that's even better. Image classification, yeah.
So video captioning.
Video captioning, that's pretty cool. Yeah, it uses RNNs well and CNN. Object detection. Object detection, yeah, really cool stuff. Yeah, so I have a few of my own. I like to see the computer beating humans at Go. Embarrassing for our human race, but anyway. This uses some heavy neural networks. There's also IBM Watson. This was DeepMind, Google DeepMind. IBM Watson that beats humans in Jeopardy. So that uses a lot of NLP, a lot of words and text. Obviously, the cool kid is the self-driving car nowadays. Neural networks for making decisions and image processing, etc. And just a bunch of others, spam detection, image recognition, stock prediction, medical applications, etc. But I want to sort of think of remember what was your first thing in your head when you heard the word neural networks?
Skynet.
What's that?
Robots.
Skynet.
Yeah, something like this, right? That's what I thought. Like an 80s rock band made of robots with brains and stuff like that. That's kind of what came in my head, or something like this, something sci-fi, kind of scary. Yeah, that's what you thought the first time. Yes, I did think this, and I was a little scared of them. But then I studied them, and I learned what they were, and I got a lot more scared because I realized it's much scarier than that. There's a bunch of dots, a bunch of lines. These things have formulas, matrix multiplication, some activation functions. Information goes through. Anyway, so I studied them for a long time because I couldn't believe that this was it. And so eventually I started seeing them in a different way. And now this is how I see a neural network. Not like this, but like this. So it's a kid playing in the sand, and there's some slightly photoshopped red shells and blue shells. And I tell the kid, can you draw a line that cuts those in two? And the kid just draws this line, and that's it. That's to me, that's a neural network. Splits data, classification, right? Yes, no. So basically like this, you have some blue points and some red points. It could be the spam emails and these the non-spam emails, or images that have a face or images that don't have a face, that kind of stuff. And your model just cuts it in two. Okay? And then you generalize, because you say, okay, everything over here I'm gonna think is blue, and everything over here is gonna think is red. So let's do a quick example just to be on the same page. We are the admissions office at a university, okay? And we want to accept and reject students based on some data. So the data, we have two columns. We have an exam, and we have grades. And so we're gonna make a model to decide if students get in or not. So we have student number 1 gets a 9 out of 10 in the exam and 8 out of 10 in the grade, so pretty good. So that one gets accepted. Then you have student number 2, which gets a 3 and a 4 out of 10, so didn't do so well, so didn't get accepted. And then we have the third one, which gets a 7 out of 10 and a 6 out of 10, and we don't know if we should accept them or not. Okay? So what's an idea of what to do to make a model like this? Like, what could be things we can do? We don't want two numbers, but we want to make a decision, right? Oh no, think way simpler. Maybe like take the average of the two, right?
Oh,
Or like the sum, or like something like that. Like maybe something like this, right? Like take a score, just add them and say, if you get bigger than 10, I accept you, right? Or like this one, Sam plus 2 times grade, or like this one. Which one there is stupid? Everyone's pretty stupid, right? Because I'm not going to subtract the grades, right? We did one in the grades, I'm not going to subtract them. So that one goes. But then which one of these two do you think is better? I mean, this one is exam plus grades, and then I check if it's bigger than 10 or not. And this one is exam plus 2 times grades. Maybe we can argue that grades are more important because exam is just 1 day, you can know whether or not, and so on. So we don't know. The answer is data, right? The answer is look at data. So graph them here. The 3-4 student goes here. The 9-8 student goes there. And this model is this line. Okay, anyone over passes and under fails. And this model is this line. So which one is it, right? And the answer is, well, let's look at previous data because we trained the algorithm. So we look at, this is all the students we have yet accepted and rejected in the past. And surprise, turns out that the line that kind of does it is this one. So it was this one, and that's training an algorithm, a simplest neural network. Quiz to see how awake we are. Does the student get accepted, yes or no? I see heads nodding.
Point out the values.
The 7 and the 6? Yes. Does the 7-6 student get accepted or not?
Yes.
Everybody says yes. Good job. You guys are fully awake. And it's 7 and a 6 is way over the line, so the student gets accepted. Okay. Great. So what if we have more data, like not 2 but 3, exam grades and maybe rank in class or something? What would we do there? Well, now we don't have a 2-dimensional problem like in a flat surface, but we have 3 columns, so we just put it in 3D. Now our data is just a bunch of points floating in 3 dimensions instead of points in a plane. And a line won't cut them, but a plane will do. So in general, if we have n dimensions of data and then minus 1-dimensional hyperplane, in that thing will cut it in 2. And that's it. But the question is, how do we find this line? That's how we train, how do we train this algorithm, right? So maybe how many of you have seen this, how to train a logistic regression? Processing with an error function, like that. I'm not a big fan of error functions because they don't tell me much. So I like to see it in a different way. And basically what happens is this, right? You have your points, and the computer just says, I don't know, I'm just going to start somewhere, and you tell me how I'm doing. So it starts here. So I'm going to draw this line, and I'm going to randomly say that this is blue and this is red. And then how am I doing? So we tell him, you're doing poorly or you're doing well, and that's what the gradient descent algorithm would be, right? And then we move this line to see if the computer can do better. So let's actually do it point by point. Let's actually ask every point how it's doing. So there's 4 points that are well classified, and they all say I'm good. And so they don't need any help. But there's these 2 points here that are poorly classified, the red in the blue area and the blue in the red area, and they need the model to be better. So what should they tell the line? Who wants to try that? Who wants to help me out? What would they tell the line? Yeah, come closer, something like that, right? So quiz, if this is the point and this is the line, should the point tell it to move closer or farther? Who says closer? Closer? Who says farther? Yeah. Closer, right? Because you want to move it closer and eventually just get it to pass you and you'll be on the correct side, right? If you've thought of an error function and take the derivative and take a step in gradient descent, this is what the step is doing, right? Because derivative is rate of change. Rate of change of the error function is this. And when you move it, basically every point is asking the line to move a little closer to it. The misclassified points, the well-classified points don't care. So then he says, I'm good. So basically, the perceptron algorithm or the gradient descent algorithm, same thing. What they do is they ask every point, how are you doing? This one say, I'm good. This one say, come closer. And then boom, listens to this point. and then this point is good, and then it listens to the other point, and then this point is good. It can listen to all of them at the same time or separately. And if you want to think about it mathematically, what this point, this line has an equation, the point has some coordinates, and it really, what really happens is you're adding the coordinates of the point into the parameters of the equation, and that's what moves the line. Any questions so far?
This looks very similar to support vector machine.
Yeah, in support vector machines, what happens is you do two things, right? Because you also want to separate the points. So your error function is not, in here the error function is how far you're from the line. In support vector machine is a combination of two things, how far you're from the line plus how separate are the two lines. So the gradient descent step does a little more than that, right? But it's basically the same thing. Okay. Cool. So okay, but something's off with this model. What if we really had a model like this to see if students were passing or failing? Do you see any inconsistency there with data? Don't think mathematically, just think like in life. Too perfect. Yeah, well, first of all, yeah, too perfect. Data's not gonna look like that. But let me give you like a bad example. Like this student over here got exam 10, perfect in the exam and 0 in his grades through school. What would you think of that person? Well, first of all, do they pass or not? Yeah, according to our slightly messed up model, the student is here on top of the line. But I would have thought I wouldn't be too trustworthy of this student, right? Maybe they copied. So we don't want to do that. So data does not look linear. Maybe we don't want to pass these ones, right? Maybe our real data looks more like this, which is much more real. Problem, not linear. So what would we do when we want to model the data that's not linear? Well, we use neural networks or other algorithms. So what's better than a line? What could we use to cut them? Maybe a curve. Yeah, maybe. Ooh, nice. So a circle could be. Yeah, you guys are way ahead of me. A curve could do. See, in the same order. Curve or two lines. In reality, a curve and two lines are a neural network, and I'll show you how. But basically, the two lines is if I delegate, like I'm not just one officer that accepts people or not, I just have like two judges. So I leave the work to judge number 1 and judge number 2. So this is judge number 1, and judge number 1 says, oh, this is judge number 2. Judge number 1 says, okay, I think the grades are way more important, so my equation is going to be 1 times exam plus 8 times grades, and if it's over a certain number, it passes. Under a certain number, it doesn't. So this one has this line and passes everybody on top. And judge number 2 says, no, I care more about the exam than the grades, you know. So puts a 7 exam and a 2 in the grades, and also picks a threshold. And it ends up accepting these people over here. Okay? And then what we do is we have a precedent that combines the knowledge of the two judges and says, I'm going to say, you know what, if both judges say yes, then I'm going to say yes. But if either one of them says no, then I reject them, and that's a neural network. Okay, we can do a little better actually. How do we get the curve? So the curve is obtained like this. If we switch from discrete predictions, which is saying I'm going to accept everything over here and reject everything over here, and instead I'm going to give everybody a grade. So the grade is, I'm going to say 0.5 for everybody in the line. That's like 50%. And then just put numbers everywhere. So if you're around here, you get very low. It's between 0 and 1, but nobody gets 0 and nobody gets 1. If you're like way at the infinity over here, you get technically 0. Way over there, you get 1. And notice that this is not a linear function because the point gets more spaced out like that, right? Like if you're close here, it changes quickly. But if you're at 0.8, 0.81, it's like super far. That's not linear. That's a sigmoid activation function. If you take the linear function in the plane and combine it with sigmoid, you get this. And so it's very important because we break linearity. We don't have a linear function anymore. And that's why now we can model data that's not linear. Okay? So now our judges give us a number between 0 and 1. And then what the precedent does, it says, okay, I'm going to take, for example, 2 times the score of judge 1. plus 3 times the score of judge 2, and then say if it's bigger than something, I'm going to pass the student. If it's less than that same number, I'm going to fail the student. So 3 parameters, right? This one, and the threshold. And then I get kind of like that kind of curves like that. So with neural networks, we break linearity on our model. So graphically, this is how I picture it in my head. We have judge 1, which says these are the students that pass. Judge 2 that says this. And then these get combined in a model. And the president says, this is how these 2 get combined. Or in other words, this is how I see them. So this is an arrow here, and this little diagram. And then judge 1 and judge 2 make, so the president makes his judgment, the judgment based on the 2 judges, and the judges made their judgment based on 2 things. Oh, sorry, I forgot. And let's say the score of the president is 2 times the judge 1 score plus 3 times the judge 2 score, so I put the 2 here and the 3 here. Okay, very simple. And then these 2 are based on 2 pieces of information, exam and grades. So if this one has the equation 1 times exam plus 8 times grades, then I put a 1 and an 8. And this one says 7 times exam plus 2 times grades, then I put a 7 and a 2. And if you're wondering where's the bias unit, it's kind of hidden, but you know, it's where you say this passes and this fails. So I just didn't want to put like a million numbers, but imagine it there.
Why did you pick those numbers?
I picked them randomly. Yeah. The idea is to start with some random numbers and get the neural network to find the best parameters. And I can, if there's time, I can show that part of the training. So that's a neural network, and that's how I see them, and that's basically how I picture them, or this, if I feel cartoonish. Okay. 2 judges and a president and some input. So we have the input layer, okay, which is the info that comes in. Hidden layer, which is a bunch of linear models. And then the output layer, which is combining these linear models using that sort of sigmoid function that I introduced. We can make this, we can change the sizes of these layers. For example, what happens if I change the size of the hidden layer? If I make it 3, well, now I can model data that looks like that. So I can make this as big as possible and get different boundaries. What if I make this one bigger, this layer bigger? Exactly, I don't have 2-dimensional data, but I have 3-dimensional data. So I have now a bunch of planes on the first layer, and then like combinations of planes and stuff like that. What if I make the last layer larger? I just have more answers, right? More outputs. So if I don't have, my model doesn't want to say yes or no or pass or fail, but I have 3 things, like for example, dog, cat, bird. I want to have an image recognition model that wants to tell me 3 different things or 4 different things. First layers are the same, and then I just put an extra layer of put more things on the final layer. But the real meat of the deep neural networks happens when you add a bunch more layers. So if I add layers like this, right? So basically, in the first one, I have some linear models. Then I have some like slightly linear combinations of linear models. And then I combine these to make more complicated models. And I can go as far as I want. I can put normal neural networks that are in the practice can be very, very deep. And here we just have a really complicated boundary. So that's it. This is how I picture now neural networks. I have some inputs, grades, exam, rank, etc., and just a bunch of people. And then the first layer is like the first layer of judges. And the second one is the ones that they report to. And then these ones are like the vice presidents or whatever, that they just take the input from the previous layer, take the grade that comes from here, combine them, and this one just reports to the CEO, and then the CEO makes a decision. And that's less scary than this, right? So when I think of this and I don't want to be too scared, I just put some faces there. And that's how I see neural networks now. So it's much friendlier. Or even better, I think that there are linear models in my first row, in my first layer, and then it's combinations of these, and then combinations of these, and then combinations of these. So things get more and more complicated the deeper and deeper you get, and you can model much more complicated stuff. So if you want a toy to play, that is amazing. How many people have seen TensorFlow playground. Isn't it the coolest thing in the world? Like, there's a bunch of areas and a bunch of points like that, and you're supposed to, you click on terrain and it starts training. You can add layers, you can add neurons. Oh, these are neurons, by the way. These are, it's called neural networks because you have these neuron things where neurons come in, information comes in and information comes out, like in the brain where you have like signals, nervous inputs comes in a neuron and something comes out. It's supposed to mimic the brain. And now we can see neural networks everywhere, right? In the self-driving car, this is an oversimplified example, but you just take your image pixel by pixel and put ones and zeros here if it's black or white. You have a huge vector, and that goes through a layer and through another layer, and then it answers turn around or brake or accelerate. That's oversimplified, but the reality is this. You have a bunch of layers. And at the end, you have things like 1,164 neurons, 100 neurons. This processes image and also many decisions. The one for playing Go is also like this. It has a bunch of layers. Okay? And at the end, it tells you what move to make. So I think of neural networks as a magic hat. So basically, you input exam and grades, and it says pass or didn't pass, right? Or like if it's a medical application, you input temperature, symptoms, etc., a vector of information for any patient, and then it tells you how it's sick or healthy. Things like stock market, you can enter stock prices, tells you buy something. Or even better, image recognition, right? If you enter this as a vector of pixels, then it tells you if it's a dog. And you can keep going. I used to work at YouTube in the recommendations, so this was kind of fun. You think you put things like age, location, etc. Did they watch Despacito video? Did they watch the Pitbull video? And then you put it in, and then it says, oh, you're going to watch the Ricky Martin video with 80% probability. Now you know my taste. Things like spam detection, you can put in the text, and this is what we're going to learn today. So you put in text, hello, it's grandma, and it says it's not spam, or you put earn lots cash quickly, and it says spam. So this is similar to what we're going to do today. So now we're going to do the sentiment analysis lab, which says the following. Basically, you have you input movie reviews, okay? And the movie reviews are along the lines of like maybe what a great movie, and then the neural network says happy, and then that was terrible, and then the neural network says sad. And so what happens is the following. We do one hot encoding. So we have the what a great movie. We just have a huge vector with all the words, and well, this is not all the words, but some of them. And we see which are the ones in our movie, so we disorganize them. This we saw with ARPAN already, but basically we take, a great movie, what, and just input that vector into the neural network magic hat, and then it says happy. Okay. So how many people have been able to? Everybody has been able to download the lab. I want you guys to this is the part where you can look at the lab, and I can walk you through it in a minute, but take a look and we'll.
Can you point out which notebook?
Oh yeah. The notebook, I don't have the name, but it's IMDb Keras. Don't look at the IMDb Keras solutions, because that's the solutions.
Just Keras, not the RNN?
Not the RNN, yeah, IMDb Keras. So I didn't write it down, but I can write it down. Right. Where did this go? No, that's not it. Sorry. Harpan, what's the name of the lab? IMDb in Keras?
It's just called IMDb_Keras. I think I removed the in.
Like that?
There is no in anymore.
Thank you.
Just reduced it.
just, this is weird because I can only present. No, let me try to not do it in the browser because I have some slides. I'll leave you guys a few minutes and then I'll start like maybe showing question by question.
But if you have any questions in the meantime,
Oh, you're downloading. I see. Yeah, the downloading part is yeah, I downloaded it while we're waiting.
How many people have managed to pass the first part of like load the data set?
That's what you're waiting.
Okay, I'm going waiting.
Progress.
While you're waiting, I can show you something. Who wants to see back propagation? How to train your neural network?
Let's do it.
Okay, let's do this. Where is it? So it's very quick. But basically, hey, what happened? Let me quickly show you how neural networks get trained, okay? So basically it's the same as before when we asked the point, what do you want? And the point says, I want the line to come closer or to stick around where it is, right? Except with an extra complication, so with two stages now. Basically we have, let's say this point. This point is badly classified because it's a blue point in the red area. So what would this point say? Right? It'll say come closer. Very nice. What about this point? So let's think. What would this point say? It says nothing, right? It could say don't move, but is there something better? It could say I'm good, right? Is there something better? It can say, like, I mean, how well classified if this point was here? How well classified would it be? Like that. Yeah, exactly, right? If it's here, it's like super well classified, right? The points want to be really well classified. So I'd really like, if it says go farther, it's actually better, right? And that's when what really happening here is you calculate the derivative and you get something of the opposite sign and it says push away to decrease the error. So what it does is this, like it just goes a little farther, believes this point and believes this point. So that's what we're going to do. We're going to figure out how to make the line go farther or closer. Like that. So we're going to do it in two stages. So feed forward is to go through the network and make a prediction. So what it does is takes the node, the grades and the test, and plots them here and plots them here, and then the president, this is judge 1, judge 2, the president combines the two scores, plots the points, and this point is very poorly classified because it's a blue point in the red area. So what does the point say? And this is when backpropagation comes into play, which is listen to the point and backpropagate whatever the point says. So the point says, come closer, okay? Which means this boundary has to come closer to the point. Now to come closer to the point, let's see what happens. Well, I have judge 1 and judge 2. Which judge should I believe more? Yeah, this one, right? This one's telling me the truth, whereas this one's lying. So this is the liar, and this is trustable, right? Or trustworthy, whatever the word is. And these the length, the width of the arrow are the weights. So how much I take this score plus how much of this score. So I should probably listen to this one more and to this one less. So I decrease the score and increase the score. Okay? If you're thinking back propagation, that's the derivative of the error function, right? So I do this. Now, what else can happen, right? I can make this one a little better by saying, come closer, right? So this line will come closer. And this means that if I want to move this line closer, this line is a combination of these two things. So maybe this one goes up, maybe this one goes down. I don't know. I was lazy to figure this part out. But something goes up and something goes down in order to move this line. And the same thing here. This one says go farther, so it moves it this way. We have to update the weights of the line, right? And so we do it in one step. That's one step of backpropagation. And things get a little better. I listen to the better judge a little more, and each judge does just a little better. And I just, and this point says, yeah, you're getting a little better there, buddy. And we do this many, 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 many times. So after many, many tries, we get to a point where our models are better and our final model is better. And that's really what backpropagation is. When you think about these arrows over here, that really was chain rule. Like, right, you have the arrows here that tells you go up or down, that's the derivative. These are composition of functions. So to get the derivative, you take chain rule. So these arrows are what the chain rule tells you. And that's it. That's backpropagation. Any questions?
So you're reducing the error.
Yeah, you are always reducing the error in stages. Right? Because the error is a combination of a bunch of things. So you reduce the error, you take the derivative of all of them.
But do you know how many steps you have to do backpropagate?
Many. Yeah, that's the expensive part of training neural networks, doing backpropagation. Because if you have like 1,000 layers, like many layers, it's a combination of functions of many really long chain rules. So that can be really expensive. So there's ways to do it in better ways. For example, here we listen to one point, right? In reality, we have to listen to all the points, but we can take them maybe one by one, or like a few by a few, like these random points, listen to them, these random points. That's quicker than taking all your set every time. So there's tons of ways to make this better or faster. Yeah. Questions? How's it going with the loading data set? Did it load? Put your hand to that. How's it?
Sorry. No,
Oh.
it hasn't.
It loaded. Okay, good.
I think you should proceed. It's not going to load for some of us.
Okay, let me just I'm a little confused with this.
Stuck.
Give me a moment.
No, it's just everybody's downloading, so the IMT set. Yeah. It was not in the thumb drive. Was it?
No, it wasn't. We thought it would be like pre-built into images, but apparently when we download on
So let's see if people.
Does someone have the thumb drive?
So most people should have gone to the loading the data thing. You should get the sizes of X training and X test. I think it's 20,000 or something. 10,000. 5,000. Okay. The next is examining the data. So maybe I can quickly go over examining the data. What happens here is it's a really like the one-cut encoding I showed you before. It's really like a two-stage thing. What it does is it puts all the words in order and picks the ones that we have. So number 1, number 8, number 15, number 23, and then just says my vector is going to be 1, 8, 15, 23. So when you run the second one, you get that review, a sample review appears with a bunch of numbers. That's it. Okay. Let me actually look at the lab here. So this, for example, right? Examining the data. The first review appears as 1, 14, 22, 16. It's just all the words appearing in the review in order. So let's go to the third. Let's go to the third one. So one hot encoding the output. What this does is it takes your 1, 8, 15, 23 and turns it into a 1, 0 vector. So it takes what I told you at the very beginning. Whoa. Right? So it takes a 1 here, a 1 here, one here, etc. And now instead of a vector of 4 things, we have a vector of like many, but that's what we want to feed into the neural network. And then we also want to encode the output. So happy and sad are 1 and 0. But in reality, we want 1, 0, and 0, 1. So this is like the happy coordinate and the sad coordinate. Sorry. Okay? So we want to encode the input, want to encode the output. And now, this is the part to do. The exercise is to train the neural network. So I'm going to give you an example of a neural network trained in Keras. In Keras, what you do is you define your model. You start with model equals sequential. That just says, I want to work with a neural network. And then you start adding layers to your neural network. Don't worry about this dropout one. Okay? That could be or could not be. It's just an improvement thing. But then the first one, you said, I'm going to add a dense of 4. And the input dimension is 3. So input dimension is 3. That's how many are in the input. This 4 is how many nodes are in the layer. And then I add a second layer of 2 nodes. So this is here. Okay? So this 3, 4, 2 are here. 3, 4, 2. So the exercise is to take this line and figure out what are the 3, the 4, and the 2. Or if it's not set, you can come up with it and think, okay, what should it be, right? Any questions? Yes?
Is there a good rule on how many layers you should have, or how many nodes you should
It's more of an art, really. You want to kind of put a bunch, and so that rather put more than less, and depends on your computing power.
Wouldn't that also have the possibility of overfitting?
Of course, yeah. So then one of the things would be use the overfitting, like for example that dropout one over there, or the 1 or 2 regularization.
I don't know. I need to
So
see my-
there's really no rule. Try a few things and see what's better. This is a very simple lab, so we don't have testing data here. We do a little bit more in that, but in reality we want to do testing validation. Okay, who can figure out? Let me figure out the numbers and I'll come by.
What are you looking for?
Question?
What are you looking for? You said what?
Yes. The idea is this is the answer. Basically, this is how you train a model in Keras. Except your job is to figure out what is this 3, this 3. So what is the first layer that I have to input my data, right? So in the student example, it was 2 because we have grade and exam. Thank you. And if we had like, for example, 10 words in the English language, then our vector would be like 10. So it would be 10, right? So figure out what this is. Then pick something for here. Feel free to add more layers. You can repeat this line as many times as you want. Okay, it's just gonna be expensive to train, take a while. So up to you. And what is this? Right? This is how many answers I want. So if I want maybe 1 thing or 2 things or 5. Okay, so one thing. do you see this line? Tokenizer equals tokenizer num words equals 1,000. What this is really doing is, I mean, technically we can use all the words, but maybe if we use all the words, like vectors are going to be huge, and some words are just going to be so obscure that are not going to be very determining of if we use good or bad. So this says we cut it at 1,000. So I'm just going to take the 1,000 more popular words and truncate my review to that. Okay? You can play with that number. You make it 3 or 4 is not nothing. Make it all maybe it's too slow to train.
So it's looking at 1,000 most popular among the data, or
Probably among the data.
okay.
This is a Keras package, so I know not exactly sure how it works, but I would say yeah, the most popular. And I'm guessing it's not too different from the most 1,000 most popular worldwide
Overall, yeah.
over IMDb. Maybe like some differences, but
So does that mean for the tokenizer has to do 2 loops through the data once to figure out what to truncate, and then the second one actually do it?
I would guess that it takes the words. Yeah, it goes from loop to see the frequencies, and the second one to pick the 1,000 more.
So do you ever run into funky memory then? Because that means you actually have to store, even though you're only going to tokenize the top 1,000, when you make the first pass through, you're going to have to keep track of all words.
Yeah,
And this is like, well, yeah, but you have to have a full dictionary in memory then.
well, this may be preprocessed already.
This is a small data set. It's only like 7.
Well, yeah, if you're using this exact training data, but as a general statement,
As a general statement, yeah, it's probably not that training.
What would you do if you don't want to do it? Just delete the tokenizer?
Yeah, just don't have it. Or there may be a flag for numbers. There's also a way to and we don't have it here, but in this package, there's also a way to remove the most popular ones, right? Because the and of it don't say anything and they just waste space. So another flag that we don't have there. Really? Another flag that we don't use here, but we could, is a flag that says remove the 10 or 20 most popular words or 5. So a lot of things to play with. So what is the input dimension then? 1,000. There you go. Very good. And have people tried training the model with different sizes of a middle layer, of a hidden layer? So I tried 512. That's what I went for.
That's what we also do.
Huh?
That's what we also do.
Perfect. Good job. Some things like softmax, relu are different activation functions. Relu is normally better. Softmax is the one I showed you today. And then what you do is model compile. So you compile the model and you get something like this, a description of your model. Don't worry about this RM prop, categorical cross entropy. These things are pretty standard, but it's the error function that you want to use, the optimizer that you want to use. Keras has some pretty powerful built-in optimizers that you kind of just put in and not worry about it. But they are methods to train your model better. And then we come to training the model. So let me see. Also, this is compile the model. That's the solution. Training the model. How many people have, who has managed to train the model? Or is in training as we speak?
Changing the backside of the box.
What?
Initially with your, it came 25 per day. Changing the backside of the box.
Okay. What came?
Initially with backside of 32 it was 10. Okay. It was 85 per day.
Okay. That's pretty good.
But now changing to backside 64.
Okay.
It was 40.
Okay. So who's in the training process? Yes. How'd you do? You got wrong? How many people are having a trouble with 3? One hot encoding the output. You getting some array error? That's strange. Ah. Oh yeah, I didn't run this.
You said they're getting a memory error?
We're getting a hard like some array error with number 3. I don't know what it is.
And mine wasn't in the solution, it's in the other one that I got. I'm in the solutions as well.
You're in the solutions notebook and it still fails.
It worked.
Oh.
The other one did not work.
Okay, can you try the solutions? Open that one.
That's what it is.
Yeah, thanks. Cool.
Some difference between them.
I didn't think there was a difference, but maybe there is. It was written by me, so there could be tons of mistakes. Sequences to matrix. I don't know. You guys see a difference there? Extrain modular binary. Here. Let me do it the stupid way. Oh, maybe not. No. Did you try the solutions? It worked? Oh, okay. So if something doesn't work, go to the solutions notebook and it works there. And then don't look at the solution. Cool. So everybody succeed at training the network. What do you guys get for the accuracy? Who evaluated the model? Let's see who can get more.
85.4.
So I already got beat because I got 82% and he got 85. Okay, 85. Anybody any higher than 85?
I'm adding more layers.
Adding more layers. Good job. Who can get more than 85? Or who can get any other number? Has he tried anything? So you'll see one thing. The more complex the model, probably the more accuracy you get. But 85 still messes up 15% of the time. I don't know, maybe we're missing something, right? What about a 5-minute break and then I'll tell you what we're missing because it's already 5. Yeah? Suspense. What are we missing? How do we make this 85 better? Can we raise it all the way to 100? Don't miss the next second. 5-minute break and then I'll show you how to make this 85 way better. Okay? And I'm happy to answer questions in the meantime if you are so eager that you want to use the 5-minute break to train your model. Yeah. Oh, because of this.
But that's what we do this.
Yeah. The video is just like the wall and some dude talking.
So what is that dropout
Oh,
layer there, or that
great question.
dropout?
Yeah, we'll do dropout while I in the break.
Okay.
Basically, here's the idea. You have your neural network, right?
Right.
Let me put the neural network in. Let me draw a neural network somewhere here. Let's say this one, right?
Okay, yeah.
So you train your neural network. Think about this. What if like this weight is humongous? Then that kind of decides.
Yeah, it's gonna dominate the entire,
It's gonna dominate, right?
yeah,
You don't want that, right?
right.
So what do you do? So my mental analysis, if I'm doing, going to the gym every day and just end up working one arm and it's really strong. So what I do is I just randomly tie this one and work with the other one, or randomly tie this one. Yeah. So
I
that's
see.
dropout.
I see.
Dropout, what it does is randomly kills a bunch of these. So to every node it associates a probability, and with that probability it removes it from the training from one step.
Mm-hmm.
So in one step of backpropagation, let's say I don't use this one and this one, and I train the other ones.
Mm-hmm.
For one step, I don't use this one, so then this one is so dominant that I just force to train the other ones.
I gotcha.
So Okay.
It's kind of a load testing in a sense.
It's kind of a what?
Kind of a load testing that you drop one node and then
Yeah, exactly. So you drop a few, backpropagate, and then you have just better models because every node has the same, as opposed to one.
In this case, are you dropping out half of them?
No, oh yeah, good call. No, I'm dropping each one of them with a 0.5 probability. So it's pretty big, right? I'm dropping a bunch. Normally, you would say a smaller probability, 0.2 or something. So you're dropping a few. Depends. It's one parameter to play with.
Okay.
Yeah.
Okay. But also, this is only happening during training. Right.
Oh yes. At the end, you return it.
And you keep everything. Right.
Could you explain what activation means?
Oh, absolutely. Do you remember? So in every stage, right, I had this continuous prediction, right? What really happening here is I take my grades and my exam, and I take a linear function of these, and then I combine that with an activation function that sends everything from 0 to 1. So the very negative number minus a million turns into something 0, 0 turns into 0.5, and plus a million turns into almost 1. So it's really a function that looks like this, right? Very negative numbers go to 0, very positive numbers go to 1, and here it goes 0.5. The formula is 1 over 1 plus e to the minus x. You can tell that for x equals very large is 0, 1, very negative 0, and for 0 is 1 over 1 plus e to the minus 0, which is 1/2. That's the activation function. It has to be nice because somewhere in the process you have to take the derivative, and the derivative of that function is beautiful, right? It could also be another activation function, for example, hyperbolic tangent that goes from -1 to 1. But then there's this other one that works beautifully for some reason, which is a ReLU, which is 0 if you're negative, and x if you're positive. So it would just be 0 for all the red, and then 1, 2, 3, 4, 5, 6. And that one somehow works very well. The reason it works very well is, check this out. Your function is like this, right? So the derivative is kind of 0 on the sides. And that's not good because you're taking a derivative. The thing is almost 0. And you're using that derivative to take steps, gradients and steps. So your steps are minimal, right? Your notes at the end get high derivatives, but the one over here, it's like chain rules of product of derivatives, a bunch of small numbers, you get very tiny numbers. And so your network doesn't train. So for that reason, we use activation functions like ReLU instead of sigma. Because ReLU has big derivatives because it's a linear. So anyway, that's a long story. The short story is which function do you use to combine with the linear function to get your answer at each stage?
And what was softmax?
Softmax?
Softmax is the sigmoid.
That's sigmoid. Oh, yeah,
population.
yeah, that's it. Yes.
But applied across. Yeah.
Yeah. So sigmoid, ReLU, tan H are the ones you normally use. As a rule of thumb, ReLU for everywhere and sigmoid for the last one is what normally works better, right?
Yeah. Typically.
if you want to do a classification, yeah. But
If you want to do regression, then remove the sigmoid at the end and you just get numbers instead of numbers from 0 to 1.
Do you see much benefit to the leaky ReLU?
To do what? Leaky ReLU? What's that?
The one where it goes
It's a new variation.
slightly below. Yeah, so instead of like ending right at 0, it goes slowly goes below 0.
Oh, does it work better? I don't know.
It depends on, I think, the domain and At the end of the day, it's like what they were trying to say is it doesn't matter what kind of linearity you have, non-linearity you have. As long as you have some non-linearity, the network will find out the appropriate kinds of weights to fit to your problem.
And I think that's the real reason of linear activation, because all these are linear functions.
Right.
You introduce non-linear functions, which are activation functions.
Yeah.
So that you convert the linear into non-linear.
Right.
That's how the deep learning network works first.
Exactly, because the thing is, if you only had linear functions, then you could replace that entire computation by a single matrix multiplication, because linear functions can be combined. Right?
Yeah, so that's why I was going to ask, where is the NLP coming into picture?
Yeah.
Oh yeah, this is where the NLP is coming. Yes, so welcome back. We left a question last time, and is how do we make this 85% or 82% or where we got better? By the way, did anybody get any other accuracies? Anyone share?
Yeah, I got a couple of more points.
You got higher, wow.
85 point,
85.
7, so I'm adding 3 more than this.
Wow, not bad.
But this sounds going beyond 85.
Pretty good. Sorry?
Around 84 seems to be
84, yeah, seems that's sort of the best one can do, I think, with this constraint. And why is it that we're not getting higher even though we're making a network train? It could just be that we're not like, that we're missing something, which is this. I expected this movie to be much better. What is that, a good review or a bad review? I think I messed it up, sorry. This movie is much better than I expected. Is it a bad review or a good review? So one is good and the other one is bad. And I don't know what I was on yesterday, but I messed it up. It's this one's good and this one's bad. Sorry about that. See, a human already made a mistake, so a computer has no hope. Anyway, so it's almost the same words, right? Because when I'm encoding, and when I encode this, aside from a small difference, because we couldn't come up with a phrase that, when reworded, changes meaning. But if you find one, let us know. Small change, but it's almost the same vector, right? So the vector doesn't say that much, because word arrangements are very important. So we need to capture that. We need to capture sequentiality in these things. So bag of words just doesn't do it. That does it 85%, and that's as far as it goes. So this is where recurrent neural networks come into play. And recurrent neural networks work like this. Let's say we have a children's book, okay? And a children's book has very simple sentences like John saw Mary, or Mary saw Spot, or things like that, right? Mary saw John. So these two sentences, John saw Mary and Mary saw John, have the same bag of words, but different meanings, because this one's this, and this one is this, okay? So how do we tell them apart? With a bunch of neural networks connected to each other in order. That's a recurrent neural network. So a neural network, what it does is it finds a vector representation of your concept. So John will become some kind of vector that I see this way. That's John. Saw will become this vector saw. And Mary will become the vector Mary, right? But what we really want is a recurrent neural network. So what it does is, this is the one for John. And the John vector comes out, feeds into another neural network, okay? And this one takes two inputs, saw and whatever the memory is, which is the current memory. Right now we have John in our head. So we see what we have plus what we just saw. And then we have John saw, okay? That feeds into another neural network that feeds in whatever our memory is and Mary. And it gets the vector concept of John saw Mary. So this is a little sort of up in high level, but get the idea, right? The idea is that this neural network takes two inputs, whatever our current memory is, plus whatever the new thing is happening, and combines them into a new current memory. Okay, so a bunch, and this is the same neural network, so it trains the same parameters. And this is for Mary saw John, so similar thing, but we fit things in a different order, and it just ends up with a different vector. Whereas the bag of words will give us the same two vectors for Mary saw John and for John saw Mary. So the way to see it is like this. We have a new word coming in, and the previous memory, and they join, and a new memory comes out. Or we can just loop it like this, and basically our previous memory and our new word combine to give us our new memory. All right? And that is an RNN. So the way I see it in my head is, well, you have a word coming in, hi, and that goes through our committee of people who make decisions and ends up with how, like the next word, for example. And then this guy just comes back into the meeting of the lower ranking and just tells them this word. So like basically you have your neural network connects back to the beginning and sends the information and keeps a working memory, okay? And then in practice, RNNs have low memory. Like if you start, for example, generating text with your phone by pressing the word that it suggests, you realize that every 2 or 3 words make sense, but the whole thing makes absolutely no sense. That's because RNNs have kind of bad memory. It's like a goldfish or something. LSTMs have better memory because they carry a long-term memory and a short-term memory, and then a bunch of weird stuff happens, and then long-term memory and short-term memory come out. But the cool thing is, in Keras, you just remove the word RNN and add the word LSTM, and it does magic. So what we do is we take first an RNN to process the phrase, and then a neural network to take this vector coming out that carries the sequentiality of the phrase into a sentiment RNN that we train now just normally, okay? And then we get things like happy or sad. Any questions so far about RNN? So a lot more high level, but like the idea is there. Even if you think about it, the training is the same. You fit in data, you do forward back propagation. The back propagation for RNNs goes through time, so it goes a few times around, but it ends up being the same thing. And as we said, luckily in Keras is 1 line of code. So now I'm going to pass it to Arpan, who will explain some differences between. We have a different lab. The lab works IMDb with sequences now, with RNNs. So Arpan will show you that.
I think you can actually download it and get started. There is one specific point that I'm going to touch upon is called word embeddings. But yeah, the notebook is called IMDb Keras RNN. So go ahead and open that. So if you have the notebook open, you'll see that the first few steps are kind of similar. You're loading the data, right? But at some point we diverge. Instead of doing the binary encoding that we were doing for regular neural networks, we're going to leave it as a sequence. But the thing is that now that you have a sequence of words, how do you fit it into, or how do you feed it into a recurrent neural network? So I'm going to talk about that briefly in this section. So far we've looked at representations that convert an entire document, and in this case an entire review, into a vector. So for the lab, you were converting it into a binary vector, zeros and ones, whether this word is present or not present. And that can be used for certain applications like, ranking something or classifying or even, identifying sentiments. But for certain other applications, including if you want to use like a recurrent neural network, you need to represent each word as a vector, right? So think about it. Before you were converting each document into a vector, and now we'll be converting each word into a vector and then passing in one vector at a time to the recurrent neural network. And the vector we want, okay, now let's think about what kind of vector we want. We want something, say, like a 3-dimensional vector, for instance, or however many dimensional vector it is. But we want it to exhibit certain properties, okay? One idea is that we want things that are maybe similar in some sense to have vectors that are close together or have values that are close together. Okay, that's just a general idea. Similarly, if there are words that don't have a similar meaning, then we probably want their vectors to be far away. And why would we want that? Because in most cases, when we're talking about natural language processing applications, we want to capture meaning that is behind a word or behind a sequence of words. So it makes sense for us to have these properties in the vector representation. And so this sort of a vector representation where the words are located in spaces that convey some sort of meaning or capture some sort of meaning of those words is called a word embedding. So the words are embedded in this vector space. And this is a simple three-dimensional figure, but it could be more dimensions. And the number of dimensions you need is typically dependent on the vocabulary size you have, that is the number of unique words, and what kind of, again, like sort of a similar idea from LDA, like what kind of underlying meanings do you have? Like maybe you have a language with 100 words, but it has a lot of synonyms, like, every 10 group of words means the same thing or something like that. Then maybe a 10-dimensional vector might just be enough, right? So that varies a little bit, but the idea is that you take words and then you come up with a vector representation that has these desired properties. One of these embeddings that has become very popular is called word-to-vec. And as the name suggests, word-to-vec transforms words into vectors, right? But it doesn't tell you how it does that, right? Okay. So the core idea that they use is that a model that is able to predict, say, you're given these words, brown fox, over the, but this word in the middle is left out, and then the model is able to predict that word. Oh, the missing word in between is jumps. If you have a model like this, or something that is given jumps and is able to predict one of these, neighboring words, then you can think that the model understands something about the meaning. And this is not just happening over a single sentence, but over a large corpus. Once it starts seeing a bunch of these examples, like I mentioned way back, I want a gallon of, and if it starts to predict either milk or gas or something like that instead of elephants and horses, then you sort of are beginning to capture the idea that, okay, a gallon of it has to be some liquid. So the idea behind word-to-vec is that if you have a model that is able to predict these things, then whatever representation it is using internally for the words should be a good representation to carry forward, to use for that word. And that's how word-to-vec models are built. Though there are two flavors. One is where you give it the surrounding words or context words and make the model predict the word in the middle, and that's called continuous bag of words. I don't know who came up with the name. The other one where you give it a central word and make it predict the ones on the side is called continuous skipgram. And I'll talk about what do I mean by make the word model predict. Okay, let's look at skipgram model, for instance. You feed in a word, okay? You turn it into a one-hot encoded vector. That's the sort of the starting point. You put it through a neural network, okay? And you've structured the neural network in a way so that it predicts 2 words before and 2 words after, okay? And like Luis mentioned, that you could have a single output from neural networks, or you could have multiple outputs. And the neural network doesn't really care what these outputs mean. It's for you to how you interpret and how you structure it. So if you structure it like this and then interpret the first block of outputs as indicating what is 2 words before, the next as one word before, this one as the next word, and the last one as 2 words after. And then you basically start training it. For instance, you put in jumps, and it, starts predicting some random words. It won't start doing this at the very beginning, but depending on those words that it predicts and the actual correct answers, you can come up with an error metric, and you can start training the network till it reaches something like this. It won't get the right answers every time, because think about it. If you feed in jumps, it's not always going to be just in this context. If you feed it a large enough collection of sentences. Yeah.
So if you're in this case, if your vocabulary is 10,000 words, the output would be something like 50,000 or 40,000 output.
No, that's the interesting part. Let me go back to this diagram. Wait. Not this diagram. Sorry. Huh? Oh, thanks. So this one, the way you're setting up the problem for word2vec is you want it to predict a limited window of words. Okay, so in this case, it's your choice. Like the bigger the window is, the more contextual or the more long-term information it'll try to build in. But empirically, they've found like either 2 words or 4 words before and 4 words after is something that usually gives good results. And I'll tell you what the good results are. The weird part is that this is just a means to an end. We'll talk about what our final goal is. Yeah.
So why is the one like in the second box? Like I don't really get the W sub T, like why is jumps like in the second box?
Why is there a 1 here? Because this assume this is the one-hot encoding for this word. Say we have, in our vocabulary, assume if we had only 4 words, and jumps was assigned this place, then it would have 1 here. Does that make sense?
So they're not like documents, right?
No, just for this one single word.
That's the one-hot encoding for that one.
For that word.
Okay.
So jumps is one input you're giving. So all the other predictions which are coming in all the predefined vector. Where the other predictions are coming from?
These words that are being produced here,
Yeah.
that's what is being produced by the neural network. And at the very beginning, say this neural network has randomly initialized weights, this is going to produce garbage. It's going to produce like the at inside tree, something like that. You tweak the word weights a little bit, it produces some other random collection of words. Now what you have to do is set up a training for this. How do you set up the training? Well, you take a sequence of say 5 words, like brown fox jumps over like that. You take a span like that. You feed in the middle word, okay? See what words it is predicting, and line up the words that it is supposed to predict. You find the differences between those word vectors. That's your error measure, and then you back propagate and train this entire network. Okay? You do this over and over with multiple such spans, just randomly selected from a corpus. And what you will begin to see is that it will start predicting at least some of the words correctly. Okay? You don't have to like do this till it gets perfect, because it's a very hard problem. It's actually a problem that is that you'll never solve perfectly, because these words don't always occur in the exact same place every time. Otherwise, the English language would be very simple and very predictable, but it's not. So you'll not get a perfect result, but once you start getting once your match score, however you're scoring this, starts flattening out, then what you do is then you take some internal slice within that neural network, okay, or whatever model you were trying to use to predict, and call that the word vector for the input word. Like I mentioned, this whole exercise is a means to an end. we are actually trying to find a good representation for jumps, okay? And what we said was, our hypothesis is that if we can come up with a model that is able to predict surrounding words correctly, or to a certain extent with a certain accuracy, then whatever representation it has internally come up with for that word must be a good representation, must be a good embedding, right?
What is the green, the green row for circle versus the yellow?
Right, so that's a good question. What are the different, layers here? You can think of this as a multi-layer neural network, okay? Where the beginning layers are doing some low-level processing on the inputs that are coming in. The middle layers are typically performing transformations that are critical to understanding what's going on. And then the last final set of layers are taking that internal representation and converting those into outputs. So here, this is just me showing an example of, you're taking the middle slice, but it could be some other layer within a deeper neural network as well. Now, the interesting thing is when people started coming up with this idea of word-to-vec, they didn't even go this far. They didn't even have such a deep, complicated neural network. They had a single layer, and what they did was they took the outputs of that single layer as the word vector itself. So you can come up with a simpler sort of setup, but I try to think of it this way because it makes, more sense to me, that you're setting up a full pipeline, and then you're taking an intermediate representation as the representation for the word. Now, yeah?
This skip-gram model makes sense, but can you explain the
continuous bag of words? I don't have a diagram for it here, but it's it's going to be very similar to this, just flipped around. So you'll have 4 words being fed in, and then 1 word being predicted at the end, right? I'm trying to recall exactly how you extract the representation for a single word, but the idea is again that if you're given a collection of surrounding words, and you're able to predict the single word from that, then maybe these surrounding words are telling you a lot about the word being predicted. So it often happens where I'll say a sentence but leave out a word in the middle, and you'll be able to guess very easily what I meant, right? So that kind of gives you the intuition that maybe there is some value to just looking at surrounding words, and maybe that's what carries the meaning for central words.
Are the words surrounding words, or are they just words shuffled from the back?
They're not. They're typically surrounding words. You take a small window, say of 5 words. You pick the first 2 and the last 2 as inputs, and I don't know if people have tried jumbling them around versus feeding them straight in. There is some value to feeding them in order, because the closer a word is to the central word, it might have more significance to it. So you don't want to lose that ordering. But also, again, this is very probabilistic, because words appear in different contexts all the time, right? So how do you come up with an internal representation that starts capturing that? And that's where these sort of word-to-vec, these word embedding models really come in. If you have enough dimensionality in the middle, then it is able to capture those different contexts very well. So 2 words can be similar along one dimension, but very far along on another dimension.
So how do you determine, for general neural network training, I think the number of nodes is a hyperparameter.
Yeah.
So how do you determine what is good enough?
Right, that's a good question. I think part of it comes back to perplexity. So because if you think about this, it's a supervised problem in this sense, but there is no end goal that you're trying to reach. It's kind of similar to autoencoders, where you're feeding in a piece of text or an input, and then expecting an output that matches the input or something that is derived from the input. So in some sense, you can think of this again as a supervised learning-ish problem. So the number of parameters you need is something that you come up with a threshold that I want this model to be able to predict the surrounding words with 0.7 accuracy or 0.7 probability, and increase the number of nodes in the middle or the parameters till it reaches that point. And then you say that that is enough. There is no clear signal for that. But like I mentioned before, you need you need a bigger vector when your vocabulary is large and when you have a lot of different meanings in the vocabulary. If a lot of words mean the same thing, they're just synonyms for different ideas, then you probably don't need as much. But I don't want to spend too much time on this because I want you to work on the lab. But a quick recap of Word2Vec is it's a robust distributed vector representation. The size of the vector is, I shouldn't say independent, but it's not directly dependent on the vocabulary. Like I mentioned, it's more complicated. It's like, how many, actual meanings are there, how many words mean the same thing, etc., will affect it. So you could have a large vocabulary, but you might be able to actually squish it down to a very small embedding size. And then this third point is very important because you don't have to do this every time. You do it once. If you do it on a large enough corpus, like, get all the text from Wikipedia and do it once, you can store these word vectors in a lookup table. And then from then on, whenever you have this word, you just replace it with that word vector and run from there. And that's exactly what some of these libraries do. They'll come with a cache of word vectors that you can use. Or you could also train it for every model. In our setup, actually, we are training the embedding from scratch because what ends up happening is if you train the embedding as part of the overall problem, then your embedding is more fine-tuned to your particular task or particular problem.
So how do you determine embedding size then? Embedding size is
Right. So it's that's why I was saying, like, this is not fully correct, but it's if you have a large vocabulary, like if you choose 5,000 words or something, you could try with something like 200 or 300 for the embedding size, see what kind of training and testing accuracies you're getting, and then empirically test and reduce. I would say that the thing to keep in mind is, since these vectors are numeric vectors, they're not integers or binary codes, each individual vector dimension has the capacity to encode a lot of information. So another way of doing it might be to actually set it as a hyperparameter and search on it. You could even do some sort of binary search, so you're not testing with a lot of different values. And the best part about this is, because this sort of Word2Vec model is generated using a neural net itself, it's sort of ready to be plugged in into a neural net architecture. As far as the embedding layer being part of your network is concerned, think about it that, for the Word2Vec model, we set up an artificial task, right? We gave it, here's a word, predict these 4 words at the end, and whatever you come up with as an intermediate representation, I'll take this as a good representation. But you could make, this prediction task the actual task that you're trying to achieve. For instance, if you're doing sentiment analysis, you put in an embedding layer there, and your output is a sentiment. So then it'll come up with an embedding that is good for predicting sentiment, right? So that's why you can, if you want, make the embedding layer part of your actual neural net architecture. Okay. Yeah.
Is it like, this is the most standard vector Word2Vec, or is it like I can have my own version and somebody can have its own?
You can train your own Word2Vec from scratch on your corpus of choice. You can also use, huh? Yes, it is. That's why you can use pre-computed vectors.
So my question was, is it like, does it have a version or is it like a stable, every time it gets a letter?
It's pretty stable. The one that is pre-computed is pretty stable now because it was generated with a specific architecture, and I think they were using Wikipedia data from a certain point of time, and it's a large enough data set that even if you add a few more documents or something, it doesn't affect the results much. It might affect the actual vector values that you get. Because if you run it again with the same data, because of randomization, because of picking, you might get different vectors, but those vectors are sort of equivalent in some sense. They'll end up showing up with the same differences and distances between them. So you could use the standard one. The reason people, another reason people train their own word embeddings is, if you're working with, like for instance, movie reviews data, that might have different sort of meanings to various words than a larger corpus would. So you get a much more fine-tuned word embedding if you train it on your own. I want to quickly mention another one. Again, don't want to spend too much time, but there are other word embeddings out there. One is called Glove, which came out after Word2Vec, and they actually showed that you don't need to set up this fancy neural net representation in order to compute word vectors. You can actually do something much simpler, which is you can try to find co-occurrence. So randomly select a couple of words and see where all, in what context do they appear together, or how many times do they appear together. And you make a matrix out of that. So maybe, that column, that row column intersection contains how often does the word coffee appear after cup, right? Coffee given cup. And you compute all of this across your entire corpus. What you end up with are, what you end up with is a co-occurrence matrix. Now you break it down into a set of vectors for the context, the word that comes before, and a set of vectors for the target. And again, you apply a matrix factorization approach to take this entire co-occurrence matrix and break it down into two sets such that their vectors result in this sort of a combination. So every corresponding row vector and every corresponding column vector, when compute their dot product, should lead to the value in the co-occurrence matrix. This is the end result you want. And if you do this for all the words in your vocabulary, then you get a context vector and a word vector for every word. Okay.
What are the context?
The context is basically, so if you have any sentence like a cup of coffee, and say you've left out the common words like a and off, then cup is your context and coffee is your target. Okay. So this is actually a little weird because you end up getting two vectors for every word. One is when it is to be used as a context, one when it is to be used as a target. But I just wanted to show this to you as an example of another word embedding. Okay. And the idea is, again, like the themes are very similar. Like you're taking words that occur together and you're coming up with vectors based on those co-occurrences. So, you have to keep in mind that the ultimate goal is, not to do this, not to compute this matrix or anything, but to come up with vectors that represent those words. And when I say represent those words, yeah.
So it is a one Howard encoded vector of cup, one Howard encoded vector of my table.
No, here the starting point is a little different. Here the starting point is this matrix, which is the co-occurrence matrix, which means, say cup and coffee occur 500 times, okay? Then you put in the number 500 here, cup and baseball occur 20 times. You put the number 20 here, and then later you normalize this row such that the values add up to 1, so it becomes like a probability. Which means now, if you feed in cup, then the probability of, the probability here for coffee should be pretty high, and the probability for ball should be low. This is the co-occurrence matrix that you can build up in a very straightforward way from a given corpus. You take an entire corpus and count basically pairs of words, how frequently do they appear, and you just put them in this matrix. Yeah.
And do you have like a window?
Well, you could basically do consecutive words. So yeah, one after the other. So yeah, just take pairwise words. What will typically happen is their effects will sort of cascade down through words, so that even words that are slightly separated will ultimately get the effects of other words. Once you have this.
But that contiguous words is a special case of n-gram model, right?
Exactly, yeah.
Say, now I will allow separation of 2, or separation of 3, and so on.
Exactly, yeah. So you could generalize this to not just co-occurrence that is side by side, right? But you can expand it further. Yeah.
So people use both context vector as well as word vector in prediction tests. Or just word vector.
Typically one of them. This was basically, when people first came out with word to vec, it was a pretty impressive result. And I'll show you some quick plots about that. But later on, because people saw that the output is so good, but how is it really learning these things, and how is this really happening? Then another research group took that apart and tried to study it, and what they basically found was maybe the word to vec model internally is doing something like this, and so why not do this directly? And so that's how they started coming up with GLOVE, and they showed some results where in certain applications, the GLOVE vectors in certain tasks outperformed word to vec vectors, things like that.
Another question that I have is, if you use word vector as a feature, then basically you will increase number of features in prediction task by embedded size. Because
right.
Previously we used just term frequencies, but now it becomes a vector.
True, but the main difference is earlier you were computing a representation for every document. Now you have a representation for every word. If you did not apply word to vec and used one-hot encoding for every word, then your representation for each word would be the size of your vocabulary. Say you had 5,000 words in your vocabulary, then your vector would be 5,000 long with a single one and everything else 0. Right? For if you wanted to do it for individual words. Now the word to vec process or word embeddings will help you shrink that down to like typically a 200, 300 dimensional vector.
Words that would like never even be together.
Yeah.
Just get cut off.
They would get cut off in this process, you're saying?
Yeah,
Or-
like when you do like word to vec, it would take it down from like 5,000 to 300.
Yeah. But the neat thing is that the 5,000 representation is very sparse. It has like a 1 in one place and zeros in every. Right, and this one is going to have like numbers that are like either 0.1, 2, 0.3, 0.5, a variation of numbers. So it better utilizes that space.
But in bag of words representation, people do use most frequently occurring words. Even if you have 5,000 people may use 100 most frequently occurring words.
Right.
But word embedding, it can reduce the size even probably more.
Yeah. No, that's true. So you could take the top 100 words, top 500 words, but even then, the vectors that are produced by like bag of words or binary encoding, they don't carry any information about the words. They're like solely dependent. They're like a signature, an identity for each individual word, but they're not related in any way. So like, cat and dog and lion. They'll have randomly separated words. So the main goal of these word vectors, as I was saying earlier, what we want from these vectors is a representation that is closer if the words have similar meaning and further apart if they're different. So let me quickly fly through this. Again, if you're interested, really fascinating paper on glove is out there. I'm not going to spend too much time on it. I am going to jump to this part where I talk about how do you use these embeddings in deep learning. Like I mentioned before, you want a representation that has similar words closer and dissimilar words further apart. But another interesting property or another way of thinking about the same thing is that you want the same difference between words. So if man and woman have the same difference in their meanings as king and queen, then you want these differences to be preserved in the word embedding space that you come up with. That's another way of sort of thinking about this approach. And this is a classic example of how you might write it out. The word vector for woman minus man plus king should actually give you queen. And the weirdest thing is that word2vec and glove actually produce vectors that do this. So if you take the numbers and you add and subtract them, you get numbers that finally represent a known word like this. That's one thing. So people have tried to think about why does this happen, and there's an idea behind this called distributional hypothesis, which basically states that words that occur in the same contexts tend to have similar meanings. For example, if I say, would you like to have a cup of blank, or I like my blank black, I need my morning blank before I can do anything, right? You're slowly getting a sense of what I might be talking about. Something else you want? But the idea is that you don't even need to put in a label here, right? Your identity of whatever this word goes in between has already been sort of captured by the contextual words. And that's why people think that might be the reason that these word2vec and glove vectors, they're both sort of using the idea of co-occurrence or words that occur together are producing such good results. And I kind of missed the animation there. But the other interesting thing is it's not necessarily predicting a specific word, but it's trying to capture an idea that might translate to, you could interpret it as tea, or you could interpret it as coffee, right? But what these sentences are capturing is that, if these sentences were all that were there in the world, then the meaning of tea and coffee would be identical, right? So along the dimension that these words, these context words produce, tea and coffee actually are very similar. But then there are other contexts, other cases in which they might be dissimilar. They might actually be further apart. If you look at it from a certain perspective, after training the word2vecs for a certain time, you will get these two vectors to come close together. But consider some other sentences like dash grounds are great for composting versus I prefer loose leaf dash. Here, it's easier to differentiate these two words. One of them matches one context better, one of them matches the other context better. So how do you capture both similarities and dissimilarities? Well, what it turns out to be is, like this is coming back to how do you figure out the embedding size, you probably need another dimension, okay? Along one dimension, if you look at it, tea and coffee are close by. Along some other dimension, you might need them to be further apart. So you add a dimension, or you increase the embedding size, and you turn it around, or you look at it from another angle, and they'll be further apart. So essentially, if you have this is just 3 dimensions here, but if you have a bunch of different dimensions, they all capture different combinations of meanings, and you can have words that are like even if they have complicated subtle meanings, you can still capture them with a word embedding. Okay, I'll leave you at this slide. It's a quick comparison of how you would feed in a one hot encoded vector, how it goes through a word embedding layer, turns it into a word vector, feed it into a recurrent layer, dense layer, and then you get a one hot encoded output, or it could be a single output for something like sentiment classification, because we're running out of time. I'll leave this here, but you can go back to the lab. If you go to the next step where you're building your model, you can use this as a reference and put in the correct layers. You need a word embedding layer,